Thank you all for being here. It's an honor for us to organize, along with Taxia, this event for FLAMINGo, with the participation of our partners, a consortium, with many projects that we invited and received our invitation. Very happy for all of you being here, and I will just give the floor to our coordinator, Alvisa BMG, but before that, let's start with Robert Metzger, the organizer of eMove, that we are here in favor of this under as a satellite event of eMove conference and fair.
Okay.
Thank you very much.
Thank you very much. Good morning, ladies and gentlemen. I'm Robert Metzger from Munich Expo. I'm the CEO and publisher, and we do a lot of things throughout the years. Everything is around the theme mobility, new mobility. So it's everything under the brand eMove 360. We do the exhibition downstairs, we do the conference, we do several little events throughout the years. It's called eMonday every month. So we bring people together in the mobility industry. That's our job and that's what we do. We have a magazine, we have a newsletter weekly. Maybe if you're registered, you might have recognized this newsletter, and that's what we do all year round. It's everything about new mobility. New mobility for us is electric mobility, it's autonomous mobility, and the main topics are battery technology and charging and energy. Target groups on the visitor side are usually the engineers out of the automotive industry, and we call them, and the other part is the professional users, like fleet managers, hotels, industry, whatever. So transportation companies. This is what we do, and we are very happy to have FLAMINGo here, and thank you very much for being with us as a satellite event. And I'm very glad to welcome you all here in Munich at the Westin Grand Hotel, which is, I have to say, it's by accident. Usually we wanted to be at the Messe München. We have had there always a big trade fair, but this year is not easy in the automotive industry for everybody, and so a lot of exhibitors, especially from the Asian side, from China, they cancelled, and then finally we decided to move over here. And I think for the conference it's even more comfortable than at the Messe München. So thank you for being here. And one big event you shouldn't miss this afternoon at 4 o'clock. We start in the room Atlanta our eMove 360 award ceremony with the eMove 360 award for electric and autonomous mobility and the Materialica award for design and technology. You're all invited to join us, and just go over there to the room. And as you're here, if you after the lunch break, maybe you have time, and you also could join us in the conference room over there, if there's still some places left for you. So thank you very much, and now I think I have talked too much already. I would like to hand over to Alvisa BMG, the coordinator of the FLAMINGo Project. Thank you very much, Alvisa.
Thank you for hosting us today. It's a pleasure to be here. And when we were looking for a place for this event, it was very fortunate for us to see how fitting this move was for our project. Although we are not specifically bringing direct innovation for the electric part of the vehicle, we are still bringing, I think, a good impact on the overall lightweightening and hence the spread of these new vehicles in the future. So, yeah. Thank you again.
Good luck with your project.
Yep.
With the event.
Thank you very much. Thank you.
Good. So, the agenda for today is split basically in two parts. Mainly, we will look through the latest results of the FLAMINGo project, and in the afternoon, after the break, we will see also how other projects with similar goals are facing this challenge of bringing electric vehicles in Europe, let's say. So again, thank you to all the projects that join us today for this final event. The Multem, the Colabat, the Flex for Crash, Mimosa. Zebra, unfortunately, Daniel will not be here today because unfortunately he is sick. And then I will summarize a bit our experience in light EV, which was a cluster of projects under this same call. So why are we here today? So as I was saying, Enlight EV was a cluster of projects all funded under this call. In the frame of building a low carbon climate resilient future, the green vehicles topics propose this call for with, let's say, not very simple requests. So improve efficiency of EV, provide affordable weight reduction with eco-design principles, use appropriate hybrid multi-material solution, apply the circular economy principle, focus also on end of life of products, and so on, and many other little small requests which make this call quite challenging. What we proposed, FLAMINGo, focusing on the value chain of strengthened aluminum composites with nanoparticles, and this was actually effective since it was granted among 39 proposals submitted under this call. We started the project in 2021, so almost 4 years ago, and we are closing the project in a few months. We are involving partners from all over Europe, covering the entire manufacturing chain for these materials. So companies and research performance covering the casting, the extrusion, the manufacturing of the vehicle at the end, because what we want to check in our project is how all the material flow develops and how to consider the different little problems that appears when you move in the manufacturing chain from one step to the other. So FLAMINGo was considering these two basic facts. So the lightweighting is particularly sensitive for battery electric vehicle, and the use of aluminum is in vehicle is growing a lot. So we want to help this growth of aluminum by providing alternatives or more alternatives on the alloy composition. So these are some facts about this growth of the aluminum use in cars and how we could tap into the slowly increasing use of mild steel on respect to the higher increasing use of aluminum. So what we want to get in FLAMINGo is basically allow some of this mild steel to be converted in car manufacturing into cast aluminum or water aluminum by using strengthening aluminum metal matrix nanocomposites. So now we will go through different topics of this project in order to understand better why aluminum metal matrix nanocomposites, how to get them extruded, into parts, how to get them casted into parts, how was the installation of in the vehicle of these components, and an overall look on the sustainability of this approach and the safety of this approach, because when we use nanoparticles, there is always this aspect to keep in consideration. So, well, special thanks again to European Union for funding this project, Axia and Exeligis for organizing, and eMove and Robert who left for hosting us. And now I will leave the floor to Abdallah for the part about why aluminum metal matrix in our automobiles. So, thank you.
Good. Yeah, thank you, Alvis, for the introduction. So yes, my name is Abdullah. I'm a doctoral researcher at Renault University, and today I'll be talking about essentially the role that the nanoparticles play in aluminium metal matrix composites, and why these nanoparticles are so important to, for us to achieve the desired mechanical properties and the desired strengthening in these materials. So I want to start off with a little bit about our department at Renault University. It's called VCAST, so it's the Renault Center for Advanced Certification Technology. So essentially this department or this research institute is focusing on both the fundamental and applied research in the field of metallurgy. And when VCAST was created in 2002, we had only a handful of personnel, there was only a handful of staff. Over the past 16 to 17 years, we've grown in numbers. Now we have 85 personnel and 15 seconded industrial research engineers. So just some facts and stats for you guys about the department. Essentially, VCAST is now one of the biggest research groups in the world and in the field of metallurgy. We have more than 4,000 square meters of laboratory space. These are just some of the examples of our research laboratories. So we have an Advanced Materials Processing Center, which we call the AMPC, and an Advanced Materials Casting Center, AMCC. You can see here some of our casting equipment. So we have the high pressure die casting here, and we've got the low pressure die casting on the other side. We have a directional casting pilot line. We have an extrusion press. We also have a green sand casting machine. And in terms of the characterization, we have state-of-the-art equipment such as the high-resolution CEM, like SEMs and XRDs, etc. So this is just a little bit about our department at Renault University. And to get started on the interesting stuff, so I've got a quick introduction about the aim or the driving factor behind why we want to introduce nanoparticles into the aluminium, or why we want to produce these high specific strength materials. So essentially, as you all know, there's increasing restrictions. So we can see that the EU aims to be climate neutral by 2050. And in June of 2022, the EU member states agreed on setting stricter CO2 emissions for the passenger, commercial vehicles, and light cars. So essentially what this means is there is a push for high specific strength materials. If we look at both electric vehicles and the conventional internal combustion engine vehicle, both can actually benefit from an increase in strength. If we look at what happens when we reduce the weight of these vehicles, a 10% reduction in vehicle weight for the internal combustion engine means that there is a 6 to 8% increase in the fuel economy. Whereas for the electric vehicles, a 10% weight reduction can actually increase the range by 13.7%. So this suggests that both the electric vehicles and the conventional internal combustion engine vehicles can both benefit from an increase in strength and lightweighting. So metal matrix can be one of the potential solutions, or one of the potential ways for us to produce these high specific strength materials. So what is actually an aluminium metal matrix composite? Essentially, it's an aluminium matrix, so the base material is aluminium, and this is reinforced with a non-metallic phase, such as a ceramic nanoparticle, which is what we'll be talking about today. So this then denotes the aluminium metal matrix composite. And these materials exhibit material properties which are very desirable to the transport industry, in particular the aerospace and automotive sectors. because they exhibit properties such as superior strength, hardness, and high elastic modulus. And with the highest strength, essentially what the link between the highest strength and the lightweighting, if we have high strength materials, it means we can have the same structural abilities or comply with the same structural standards, but using less material. So that's how we can reduce the weight. So these are just some examples of where already the metal matrix composites are used in the industry. So you can see, for example, in the automotive industry, they use the spark plugs, gearboxes, and brake rotors, whereas in the aerospace industry, they're used in turbine blades. And you can see that in 2022, the global metal matrix composite market was approximated to be around $1 billion in value. It's expected that in 2030, this will double to approximately $2 billion. So there is a lot of demand for these materials, a lot of research and development taking place for these materials. So essentially, on the FLAMINGo project, as Alvis already mentioned, our aim is to produce aluminium composites for the use in the body in white for electric vehicles. So this is through extrusion and green sand casting, for example, through the casting of components. So a little bit of background on the theory behind metal matrix composites. Essentially, there are 4 key strengthening mechanisms associated with metal matrix composites. I've listed them out here, so you can see here. And in the next few slides, I'll go into a little bit more detail on each one. So we have the Hall Petch effect, or the grain refining effect. So this is when we have finer grains due to the addition of particles, and this increases the strength. The Oron bowing mechanism is the second strengthening mechanism, which is related to the dislocations bowing around the particles, as you'll see in the next slide again. And the third one is the load bearing effect, or the load transfer effect, which is related to the load being transferred from the softer matrix to the harder ceramic material. And the fourth one is the thermal mismatch between the reinforcement and the matrix. So this is related to the coefficient of thermal expansion coefficient being different for the particles as it is for the aluminium matrix. So let's look at these in a little bit more detail. We'll start off with the Hall Petch effect, or the grain refining effect. Essentially, when we add these nanoparticles to the aluminium, they can sometimes act as nucleation sites for the grains, and they can also hinder the dislocation point. So because of this, what we can produce is a finer grain structure with the addition of the nanoparticles. So you can see this is without the addition of the nanoparticles, the grains are very coarse, and once we add the nanoparticles, the grains become much finer in size. And essentially what this means is we can increase the yield strength. You can see here, this is 1 over the square root of the diameter of the grains. So this is, as we decrease the grain size, then we can see an increase in yield strength. And this is the equation which we can use to essentially model or predict the increase in strength due to the grain refining effect. So you can see it's inversely proportional to the square root of the diameter of the grains. So essentially, as the grains get smaller and smaller, then we see a larger increase in the strength. And the second strengthening mechanism, which I mentioned, was the Oron bowing mechanism. And essentially, this is where we have these dislocation lines which move in the structure as you deform the material. When they approach these hard ceramic particles, what happens is they tend to bow around the particles, as you can see, and that's why it's called Oron bowing mechanism. And this action of bowing essentially creates this ring around the particles, which then makes it even harder for the next dislocations to move. So essentially what we're doing is we're hindering the movement of dislocations through this effect, and that's why we see an increase in the yield strength due to the Oron bowing mechanism. And again, it can be modeled mathematically. We can predict the increase in yield strength due to the Oron bowing mechanism with this equation here. The third effect which I mentioned, or the third strengthening mechanism which I mentioned at the start, is the thermal mismatch effect. So this one's a little bit harder to explain, so bear with me a little bit. Essentially, we have, this is a particle and the aluminium matrix around it. This is in liquid state. There is a difference in the coefficient of thermal expansion between the ceramic particle and the aluminium matrix. And because of that, during the solidification process, when we go from the liquid to the solid, there is a difference in the shrinkage of the particle compared to the shrinkage of the matrix. So what this means essentially is we have the matrix in the solid state as we solidify it. What happens is it shrinks differently to the particle, and because of that, there's some deformation around the particle. This deformation leads to the buildup of dislocations, and then essentially what we get is something similar to the string hardening effect. And that's how we can increase the strength with the difference of coefficient of thermal expansion between the two materials. So you can see here the equation predicts the number density of the dislocation. So this is essentially how many dislocations there are. And the more dislocations, of course, the more we can increase the strength, the more the increase in strength is. So you can see the density of the dislocations is directly or inversely proportional to the particle diameter. So essentially, the smaller the particles, then we see a bigger or a higher dislocation density, meaning a greater increase in strength. So this is why today we're talking about nanoparticles, not micro-sized particles, for example, because the smaller particles give us a larger increase in strength. And the fourth and final strengthening mechanism, which I mentioned at the start, is the load-bearing effect, and this one's nice and easy to picture or imagine. Essentially, we have a matrix, as I mentioned at the start, and we have the reinforcement nanoparticles, which are in the matrix, distributed in the matrix. So when we apply a load to the material, which has the particles and the matrix in it, this load can be transferred from the softer aluminium matrix material to the harder ceramic material. Because of that, then we'll be measuring the strength of the ceramic material. So that's how we can achieve the increase in strength. And the increase in the yield strength is can be modeled with this equation due to the load-bearing effect. So essentially, these parameters here, these are the aspect ratio of the particle. So if we have a particle which is equiaxed, or let's say very globular, then the equation simplifies to this without the length or the aspect ratio parameters. So this may seem very nice, and we can, yes, achieve increases in strength, and everything seems to be easy. But actually, there's a lot of challenges associated with aluminium composites as well. So I'll talk a little bit about the key challenges which we've faced, or which are typically faced also even in other studies. There are kind of four key challenges associated with aluminium composites. The first one is the particle agglomeration. Then another key challenge is the macrostructure and homogeneity. So this is on the macro scale when we're actually casting the material. The wettability is another big challenge, and the particle stability. So we'll take a look at each one of them in a little bit more detail. So particle agglomeration. Essentially, particles are the particles that we use are nanosized. They're very small in size. And because of that, they have a very high or very large surface area. And when you have something that has a large surface area, we have high van der Waals forces of attraction. So because of that, the particles tend to kind of stick together, cluster together, agglomerate or aggregate, if you like. And then we get these kind of structures which we find in the material, which is very large sized agglomerates. And what this essentially means is there's no homogeneity to the material. So we see, for example, this agglomerate in one area, and in a different area we don't find any particles. So because of that, that leads to a decrease in the strength, or we actually see the opposite effect to what we're wanting to see. The second challenge which I mentioned was the macrostructure and homogeneity. So with particle agglomeration, that was on the micro scale. We're looking at the microstructure. Here we're talking about the macrostructure. So this is during the casting or during the processing. So essentially, this is due to the difference in densities between the particles and the matrix. I've given here some examples. So titanium carbide and boron carbide have densities of 4.93 and 2.5 grams per centimeter cubed, whereas liquid aluminium has a density of 2.6 grams per centimeter cubed. So you can see, for example, in the case of titanium carbide, the density is higher than the density of the liquid aluminium. So what we see is this particle sedimentation. During the processing, particles sediment in the liquid aluminium. The opposite effect is seen for the boron carbide because it's lighter than the liquid aluminium. So what we actually see is the particle flotation. Particles come up and they don't want to stay in the material. The third challenge is the wetting, the wettability. And this is related to how the liquid aluminium behaves around the ceramic material. So essentially it's looking at the interface between the ceramic material and the liquid aluminium. We want the best possible wettability so that we can have ease of incorporation when we add the particles to the aluminium matrix. So you can see this can be tested through the CSR drop test, for example, where we can drop the liquid material onto the substrate. And this here is very good wettability, so this is what we want, because you can see that the liquid material is behaving very nicely and wetting the substrate very well. This is very poor wetting. This is not what we want. So the fourth challenge is the particle stability. And essentially when we process the material, it has to be in the liquid state. So we process at high temperatures because we have to be in liquid aluminium temperatures. And because of that, the particles can become thermodynamically unstable. So once the particles become unstable, then they can react with the aluminium matrix, or they can even react with some of the alloying elements which are present in the alloy, and they can create undesirable phases. So you can see here, for example, I've given the some phases which can be created if we add, for example, carbide particles to the aluminium. Aluminium carbide is one of them. It's quite a common phase to see when you add the carbide particles to aluminium. And this is an unstable phase, and it's actually very brittle, so it creates the opposite effect. It reduces the strength of the material. So we try to avoid the formation of this phase when we add carbide particles to the aluminium. And so this is kind of a summary of the challenges. And I won't leave it here. I'm not just going to give you troubles and say you don't know what to do about this. No, there's solutions. We can actually tackle these problems through the processing techniques. So essentially, the powder which we receive, the powder which we add, the nanoparticle powder, is high energy ball milled by MBM, our partners, the project partners. And it's high energy ball milled with aluminium powder. And essentially what this does is it embeds the particles, the nanoparticles, in aluminium before it's introduced to the melt. So when you high energy ball mill, for example, let's say titanium carbide with aluminium powder, these titanium carbide particles are already embedded in the aluminium powder. So when we come to incorporate it, we don't have the issue of wettability because we're introducing an aluminium interface to another aluminium interface. As for the other challenges which I mentioned related to the sedimentation and the flotation, what we can do is we can apply mechanical stirring. So this is essentially where we use a rotary stirring device. You can see here, so an impeller, for example, and we mechanically stir the composite melt. And this provides a homogeneous distribution on the macro scale so that we don't see the sedimentation or flotation issues. And on the micro scale, what we can do is we can use ultrasonic melt treatment. So we apply ultrasound waves to the melt to break the smaller agglomerates, which I mentioned at the start. So those smaller sized agglomerates, which are seen on the micro scale, we can break them up using the ultrasonic waves through the cavitation effect, for example. And then we can achieve a homogeneous structure completely overall on the macro scale and the micro scale. And these are some of the examples of our work on the FLAMINGo project. So we had the direct chill cast billets extrusion, the pilot line direct chill cast billets, which were produced by our partners in Stellium. And then these were extruded into these profiles. Our partners at ODE produced a steering knuckle, which was produced through green sand casting. And of course, with the contribution from all of the partners, as I mentioned, for example, in the end, they high energy ball milled the material, we processed the material. And so everybody's involved in the production and the success of these materials. And thank you to all of the partners involved, and to the organizers of the conference. And that's it.
Are there any questions now for Abdallah? Yeah, please go ahead.
Thank you for a very interesting presentation. You talked about the static properties of the metal. Do you have any experience about the fatigue behavior of these kind of particles when you put inside the metal, so there is some influence in the crack propagation and some limitations to the mechanical components in that way.
Yeah, so on the FLAMINGo project, we haven't yet tested the fatigue properties. We expect that potentially the material may either remain the same, or there may be some decrease in the fatigue property, because as you know, these particles can act as you said, initiation sites. There is definitely a trade-off. So we see an increase in strength, there might be a reduction in fatigue, we don't know. Yeah, it's not clear. Even, for example, there are ways that we can work around it. If we have a very homogeneous distribution of the particles everywhere, then it's unlikely that the particles, because they're so small, it's unlikely that they can really act as these initiation sites. If we have particle agglomerates, this is more likely that they create these weak spots in the material, and then that can lead to worsen fatigue. But this is something definitely that is currently being looked at. There are studies on it, and I think even for our project is something which is interesting. Sure.
Okay, thank you.
Thanks.
You said that you don't give an emphasis in the rotability between the particles and the modular volume because you follow because you follow this solid state reactions and mixing with hydrogen. But at the stage, the aluminum will melt.
Yep.
So, is there any problem of the affinity of nanoparticles and the molten aluminum at this stage?
You mean when the aluminium around the particle melts?
Exactly.
Yeah. So because there's already a contact between the particles and this aluminium which is melted, actually when it's molten it has better wetting. So the wettability is related to the temperature. If we have a higher temperature, it's more fluid, it's more likely to have better wetting. So once it's in the liquid state, it should actually have better wetting on the particles. But yes, different ceramics have different wetting behaviors with the aluminium. So for example, alumina, as we found out in our project, is very poor wetting. So when you try to add it, it's very difficult to incorporate. Other carbides, well, alumina is an oxide, but carbides in general have better wetting than the alumina. So for example, we tried titanium carbide, we had very positive results because we saw that there was good wettability. So usually, yes, the high energy ball milling is one way to overcome this wetting issue, but also choosing the right material to start with has an impact as well.
Usually aluminum oxide and titanium oxide are round particles.
Yeah.
The carbides are more irregular in the shape. Does this play any role?
Yeah, so you mean the oxide around the
The oxides are around ticking, cycling, let's say, like spheres. Particles with one carbides usually are more irregular. So is there any relationship between the shape of the particle and this phenomenon?
I'm not actually quite sure. We haven't looked at this level, this scale, a very small, scale to look at the, for example, if there's one atomic layer or something. I'm not quite sure. But even if there is an oxide layer, sometimes this oxide layer actually helps with the wetting. So, for example, in the case of silicon carbide, we find the silicon carbide oxidizes, it becomes silicon oxide, SiO. So there's some oxidation, SiO2, I think actually. And this actually helps. This helps with the wetting. This facilitates better wetting for the silicon carbide particles. Sometimes the oxide acts as what's the word? As a surfactant, if you like.
Yes, but surfactant, I think that they will not start at this level to work when we met
There we go.
compose probably.
He's speaking about silicon oxide
As a surfactant. So,
back to the morphology of the nanoparticles, since these are synthesized, particularly the zinc carbide is synthesized in the matrix, in the matrix, they are roundish. They are not, I will not say perfectly spherical, but they are not right. So the overall shape is small. Later on, there will be some picture.
Yeah. But it's an interesting question. Thank you.
I would like to ask you how is the porosity in the final composite? Also, how do you deal with the possible alumina formation around the powder, right? Particles of aluminum. I suppose you are using pure aluminum particles, but I don't know if you mentioned it. And also, how is the elongation behavior if you perform tensile tests to your new composite, aluminum reinforced composite, right? Because I suppose you improve the yield and the maximum strength, but then I suppose the elongation is going to be decreased, right? So
Okay, so I think the first question was on porosity.
Yeah.
So the porosity naturally will be more in the composite material than the base material because it's been processed through mechanical stirring and these kind of things. We then apply the ultrasound, the ultrasonic waves, which actually decreases the amount of porosity in the material. There is the cavitation effect and the streaming effects, which actually reduce the amount of porosity in the material. So finally, in the end, once we apply all of the processing, then it's similar between the base and the composite material. I think your second question was on
how do you deal with alumina, possible alumina formation?
Yeah, the formation of alumina, essentially what during the processing, we apply a cover gas, apply some argon, to keep everything inert and to avoid the formation, but there's always going to be some formation of oxide. It helps, it does help, the use of the argon gas, but yeah, eventually there is always more oxide in the composite than there is in the base material. Your question on the elongation is very interesting. We're actually doing some work now to look at this trade-off between the elongation and the yield strength. We saw that once we heat treated the material, so we had cast the material and we tested in the as-cast state, and there was an increase in the yield strength and a decrease in the elongation. We then deformed the material and heat treated it, so we extruded and heat treated, and then we saw actually that the elongation at that point was very comparable to the base alloy. So we saw there was an improvement. And the reason why I think that is because there may be some phases precipitating on the particles during the heat treatment. So some precipitates, for example, we have the H2020 precipitates and we use the 6000 series alloys. These may be precipitating on or nucleating on the particles. And because of that, we have a nice interface between the particle and the matrix, improving the elongation. This is something which I think with composites in general, there's been many studies to address this issue. Some people talk about the distribution of the particles, but anyway, we can have a conversation after because I think it's quite lengthy. Okay.
Thank you very much.
Thank you.
So I want to welcome Christian Neisel from Moki for the next presentation. Christian will present the advanced design and manufacturing process of cast aluminum metal nanocomposites.
Okay. My name is Christian Neisel from the Austrian Frontier Research Institute. And my colleagues are Thomas Babel and Dr. Becker. They're together working on this project the last 4 years. I'm quite happy to present these key features of the FLAMINGo project at the AMOVE 360 today in Munich. The title is Advanced Design and Manufacturing Process of Cast Aluminium Multi-Material Nanocompounds. There is a short overview of the project. We started in 2021. It was a term of 48 months, and the value was 44 million euros. We are altogether 10 partners distributed over Europe. That are here, the most of them, and you can see it on this map. The next slide, you can see, this slide shows the project structure. We have two foundry in the project. two pilot foundries. When you have the presentation before, it was the Brunel University and the Austrian Foundry Institute in Lyon in Austria. The Brunel University was in England, in London, established. The goal was two aluminium parts that should be topology optimized. Our part was the casting part, the other one was the extrusion part. There should be weldability. This leads in a communal vehicle from the company Alke. The advantage of these parts is recyclability. That leads in a secondary aluminium in the foundry, and you can produce some new components. This was the communal vehicle. It's fully compliant with regulatories for operation on public roads. Our primary goal is to optimize the component design through a light aluminum casting. That should lead to the same mechanical property as the current one. This was a steel one with working steel. It's quite a mass-produced component. And this component is served through 100 parts. And it's a weight of 6.3 kilograms. The next step, we have to do some preliminary tests. For this, we use the software RTI Inspire that we designed an I-beam and optimized this topology to maintain the same stiffness. The result was a truss-like, a framework structure that mimics the same properties as the original beam. We use on our 3D printer to perform some horizontal distributed molds that have to produce this sample. The I-beams, the casting, were used with the aluminium 7 magnesium 3.3 alloy, the A3560 alloy. This is a standard alloy for casting parts in the automotive industry. We observed the same stiffness of maximum elastic force for the I-beams. And they were identical for the truss beams, and we achieved the advantage of 25% weight reduction. With this result, we go in the FAM analysis, as you can see in this animation. Yes? You can see the FAM simulation of the truss, like the framework. As you can see, the highest load cases are on the red zones. As you can see in the next, it fits very well with the casting. The casting was, the test of the casting were performed with 6 pieces of the SKS state and 6 pieces in the T6 heat treatment state, and they both have the same stiffness. Afterwards, we can apply these results for optimize the mechanical properties for the steering knuckle. The company Alke give us some information about the maximum steering, the maximum suspension, the maximum braking, and the lateral force. With these forces, we designed 4 load cases for simulation. And several FAM analyses were conducted by adapting these load cases to multiply preliminary tests to refine our simulation to achieve the desired level of topology optimization. As you can see in the tensile compress stress, and in the next step for the FLAMINGo stress, that you compare the material lead strength for multi-axial state of stress in the scalar equivalent stress. The next slide, you can see on the left side the FM simulation for the original steel part, and on the right side, the first topology optimized aluminum casting. This comparison allows us to access the improvements of the weight reduction and the mechanical performance of both parts, and the validation of the efficiency of our approach and meeting the project goals. Then we adapt the casting system. It was designed by the software RTR Hyperworks. The first mold is a 5-piece mold for sand casting, and the casting demonstrates a weight reduction of nearly 50%. Here are the interaction steps from the 3D design to the component casting. The process began with the 3D design of the topology optimization part. After refining, we move to the casting state. Between, we make some numerical simulation, a mold design, and construct some mold for our 3D printer to cast the steering nut. The next is why does we use the aluminum metal matrix nanocomposite. Because of the weight reduction and the material usage, we enhance performance and save energy emission to use the recyclable material. These are the nanocomposite master batches. As you can see, they were delivered by MBN on the material Italia. The production is by high energy ball milling. And why do we use it? We use it for safety reasons. So the handling with pure nanoparticles is very dangerous because of the airborne. It can be very dangerous for health. In this case, the nanomaterial is in the aluminium matrix, and we can steer it in the alloy. Here is the process, the fabrication techniques. We use an ultrasonic heat unit for disperse the clusters, and we also use the high energy steering by a modified impeller to have the effect that the particles were distributed homogeneously in the metal. The next step, we have a process for the low pressure die casting or industrial concept. It's quite nearly the same you see before. We need to choose 7 steps. It started with the welding, then with the rotation decasting to clean the melt. Afterwards, we skim the rust. Then we introduced the master batch by mechanical steering. We modified the impeller, the rotation degasser, uses also the ultrasound, and skim the rust before we start with the process of the low pressure die casting. Then we have taken some sample from the specimen and from the casting also. Here you can see images from the scanning of transmission electron microscopy from the A356 alloy with the particles, with the silicon carbide particles. On the left side you can see they are quite good distributed, and in the zoom image you can see the particles with a size less than 70 nanometers. Here you can see the hardness effect of the casting. These are the results of some tensile tests and some testing the hardness by Vickers hardness. We started with a solution heat treatment with the samples without nanoparticles to see the effect of the hardness in the heat treatment. In the samples without nanoparticles, it's mainly due to the formation of thermally activated precipitation. These precipitations are not temperature stable, which you can affect the long-term performance of the material. In contrast, the hardness of the samples with nanoparticle is due to the presence of homogeneously distributed viscous solids. The difference is the temperature stability of the nanoparticles, as the hardness remains relatively constant relative to the heat treatment. The stably precise effect of the successful incorporation of the nanoparticles during the casting, as you can see in the table, in the picture with the table slides. Then we performed different design of casting. As you can hear on the upper side, here is the first casting with a significant natural savings and improved mechanical performance. And in the upper side, there is a more casting more efficient throughout the production process and the casting technology. This leads at the end to a casting with a weight reduction of 60% that will introduced in the vehicle now. We use advanced materials such as the metal matrix composites to design more structured parts with a bionic design, and on the end of the day we have 4 out of 3 airborne parts that reduce the weight to 1.80 kilograms. At the end of the day, we have a more significant advantage to the green vehicles. The validation improves the vehicle performance and the sustainability, compromising the future of the lighting composites in the automotive engineering. And the short-term impact of the vehicle from the company Arke is that the compatibility for more off-road roads, enable more function for the utility vehicles, increase the working area of the fleet, and enable more flexibility on the vehicle configuration. Thank you for your attention. If there are any questions.
If there are no other questions, then I will.
There is a question.
Yeah.
Christian,
Yeah.
my question is very simple. Based on your experience, how possible is that this technology will be adopted by the industry?
The complex part is the production process. Yeah. I think there is on the market as an alloy that leads also included these particles. I think the industry is interested on these parts. When we have a possibility to get a production process in more industrial scale, this leads to a next project or more advantage to produce these parts.
So you don't think any considerations for the use of nanoparticles for the industry, workers, etc.?
Maybe they can use the package from NBN for industrial scale.
This will be good for NBN.
Yeah, because I think the complex part is the introduction of these patches. Yeah, as we know. Yeah, this is the biggest part of the production case, of the production chain. Yeah, thank you.
Thank you, thank you.
Let's continue with Lamberto Salvan from Arke that will present the FLAMINGo validation cases.
The green light. The last,
Okay.
yes.
Okay, so we have spoken about materials. We have seen how the different components have been built, problems behind, and the next step, the last step, is to understand how end user can apply these new materials, new technologies. I'm from Alke, producer of professional electric vehicles, and we have been selected to be the partner inside the FLAMINGo consortium in charge for the final validation of the developed technologies. A few words about Alke. Alke is a company based in northeast of Italy. We are an automotive OEM. We make electric vehicles since 25 years. We have 25 years of experience in the industry, and the focus is on transport, logistics, and special applications. So we don't make cars or passenger vehicles, but the focus is on compact vehicles for professional activity. With thousands of vehicles delivered in more than 45 countries and a multitude of variants. The specific approach that we have is to deliver platforms very flexible in terms of customization of the cargo area to fit the different application, different fields of usage. The ATX model has been chosen as the demonstrator vehicle to validate the technologies, and moving to the chosen platform. Originally, the baseline model was the ATX3, that's the present commercialized platform. But in the beginning of the project, we have moved, making several considerations. There was a new platform under development that was able to provide us freedom also to operate in real time during the project in design modification of the vehicle. So we have chosen this new platform, the ATX4, to be able to have more capabilities to change also some components to be adapted to the new technologies developed. The new platform is the result also of a parallel project that just finished, that's urbanized. This project focus was on modularity, passing safety, and efficiency. What was missing was the lightening of the vehicle that was the target, the goal of FLAMINGo. So there was synergy about, even if the approach was parallel from very different approach, but at the end, the combination of the two things, the two goals was to improve the final result of this new platform. The demonstrators items. We have spoken about extrusion, about casting. The goal was to select within the list of components of the vehicle to find the right demonstrator items for both processes. So we have selected at the beginning of the project about a dozen of components and narrowed the choice, and we arrived at the end to basically two that have been extended to 3 items. The steering knuckle that has been presented by Yogi just before, and the rear frame made by extrusion, and a third smaller item, the suspension cylinder cap made by casting. That's the number 3. The steering knuckle, the original component was made by steel, and thanks to topology optimization, we have improved the shapes and the weight. That's an important point to reach this result. The pointer is the right one, yes. So here you see the final result, the final component, and the full assembly is mounted here and mounted here on the wheel hub. That's the position where the steering knuckle is located within the project. In the front part, you see here the assembly of the subsystem and the assembly within the front part of the vehicle. The second item is the rear frame. So starting from an original frame made by steel and moving to aluminum-based frame with nano composites. They are upgraded with nano composite application. Here you see everything has been tested also for FPM to be sure that the new solution was compliant with the original one. Here you see different parts and the final assembly. The final result, that's the rear frame that has been assembled within the vehicle. This is the vehicle and location where the different demonstrator items has been assembled. The steering knuckle is in the front area, so just below the bonnet here, where the steering system, suspension system is installed. The rear frame is here is black, but is located all over here. And the suspension series cap is in the rear suspension system, so it's double in the rear part here. The goal and the work carried out by ACE was to validate the different components. There was different steps of validation. First, to understand if the new materials applied to the new components were delivering the right result in terms of mechanical properties and so on. That was made really in the first stage together with the materials developer and also the component developer's partner. So here mechanical properties. Another level was the processability when applied to automotive components. You can have the best material, best properties, but if at the end you cannot build the components in the right way, that's not usable. So the machinability of the profiles, we got, for instance, for extrusion from constellium samples within the duration of the project. That was needed to check the possibility to have different, to be used in the different machining centers, so laser cuts, CNC milling machine, and so on. Weldability, application of rivets, threads for the integration of, in this case, the support drivetrain arms and blades, but also many other brackets that are needed to the assembly of the plastic body and the cargo area and so on. And of course, the dimensional check to detect any misalignment and twisting, so tolerance issues and assembly compliance. Here you see different particular details for this is the riveting part, welding part, and so on, and different items installed on board of this subsystem. The dynamic text is the second part. Some has been carried out, some is still ongoing. So there is a multi-level analysis to evaluate the usability and performance of the new FLAMINGo materials. The verification on the road of the behavior of the different components using in-vehicle sensor. Here in this picture, you see the steering knuckle, not assembled. Here is in a separate picture with all sensor system that is integrated with a full IT setup with computer to be installed on board and so on, to have the real-time reaction and dynamic analysis, the dynamic behavior during driving of the different components. This is made on the steering knuckle, but the same is done also on the rear frame. So real-time data, but also there is in parallel we have a cloud monitoring system that you have the full geo-tracking and detection of acceleration, deceleration of the vehicle. And there is a second stage of post-test analysis that is made comparing the data collected in real time on board the vehicle and the matching with the route record to understand why behavior was generated on the particular item compared to the presence of a street bump, an acceleration, or not braking, heavy turns, and so on. That's to complete and make more more rich, let's say, the analysis of the dynamic text. What we have found, okay, here you see different so onboard devices to be used, the cloud platform for the monitoring, and different devices used for this purpose. Some conclusion, so preliminary test and statistics have seen positive results with a good ability to replace the currently used materials with new ones in terms of workability and integration into an industrial vehicle assembly process. The dynamics test will be completed within the month of November, so we are still working on that, but the preliminary results are aligned with the static positive feedback already obtained. An extra positive element delivered by the project has been the possibility of integrating the benefit of gained by the light material delivered by FLAMINGo, adding by parallel new topology optimization procedure to maximize the weight reduction. Let's see that you can have like a lighter component, but the topology optimization was delivering extra benefit because each material is linked to a particular application, to particular usage. Let's say that you cannot, for instance, we have the rear frame that was made by steel. The new component have a different shape. Clearly, the attachment points are the same, but the general shape is different. The same for the steel knuckle. Attachment point the same, but the shape is totally different. Because different material brings to different solutions. That's why it was interesting for us and useful to use the new platform, giving much more freedom also in changing the design of some attachment to maximize the result obtained by the development made in a middle stage at component level. So that's all from our side. And, yeah, we are happy for collaborating this project because for us it was totally new. The transport industry usually work with traditional materials, not looking too much to lightening and so on. So for us it was very helpful to change our mind, looking in lighter materials, and this new solution was very helpful. And, yeah, so thanks for everybody. If there are questions, I'm here for that. Thank you.
Up next is Alana España Fernandez from Global Factor, and will share the circularity approaches in FLAMINGo.
Hello everybody, as an introduction, I'm Alana España from Global Factor. In Global Factor, we are a sustainability consultancy and we manage environmental assets. And we were born with climate change and CO2 accounting into our DNA. And part of our contribution to this project is the environmental assessment, for the life cycle assessment and the life cycle cost assessment of the project. So we are in working package 8, and we're going to be speaking about the circularity approach and the sustainability aspect of the proposal. When we're speaking about the sustainability aspect of the proposal, we're going to be running through the environmental aspect that we're going to be focusing more deeply. And then there's also the economical and the social aspect. And for the social aspect, we're going to be speaking about the human aspect with the contributions of ISQ for safety. So as we've been running through in previous presentations, so our DNA as a project is also very based on the circular approach. The linear consumption, when we're speaking about the linear business model, we're speaking about take, make, use, dispose. So for the specific case, it's going to be the outside binding, alumina refining, the smelting, the aluminum, the fabrication of the parts, manufacturing of the parts, and then for the equipment manufacturing and the final trial for the vehicle. Here we have partners in every different stage of the process. So that gives us a value chain approach into the project. So from MEN, as we saw, from the nanomaterials, and then the manufacturing from different partners, from the reliability to the final demonstrator that we just saw for the vehicle, and then integrating the last part of the value chain for the recycling with Campacas. So that way we can circle in all of the different stages, and I think it's one of the strengths of the project. This helps us maximize the circular economy approach of electric vehicles, where we can optimize the recycling of components, and this way we can reduce waste, conserve resources in the value, economic value longer time, and extend the life cycle of valuable materials. So this is part of our circular approach. When we're speaking about life cycle assessment and life cycle costing, we're taking standard ISO methodologies. So we're speaking about the 14040 and 14044 methodology for life cycle assessment, where we evaluate the impacts throughout this value chain in the different stages. So on the right, you can see our focus. It's going to be the vehicle. We did some individual analysis on the components that we've been speaking to, and then how these encompass the overall vehicle assembly and on the use phase, which has a very high highest impact on the overall. So to do this life cycle assessment, we have to establish a functional unit. For these, we took into consideration PCRs, that are the product category rules. These are for electric vehicles, are under construction, but this gives us a guide to take into example, for example, the lifespan. Then we're taking these 3,000 kilometers of distance in use for 10 years. And this makes it more comparable to other studies that are going to be in the future for electric vehicles. These are just some considerations. The gross capacity, we're taking the one from the IC vehicle, that's 21 kilowatt hours, and the consumption ranges from 012 to 020 kilowatt hours per kilometer. So for our base model, we're taking the midpoint as the average for this one. And in the scope, we're taking a cradle to cradle approach, since we're going through the different stages that we just mentioned, and that this takes into account freights, manufacturing, use, as I mentioned, as an important aspect, and the end of life of the vehicle. We assessed 16 different impact categories. Among these 16 impact categories, climate change, I think, is the one that has most, is the one that is most used generally for CO2 emissions. But there's also water use, ozone depletion, fossil fuel use, and we evaluated these 16 categories and took into account 3 different scenarios for the 2 pieces that we've been speaking about and the vehicle. Our first scenario was taking into account the steel base, where we consider a 30% recycled content for steel, that we know other manufacturers of steel in the automotive industry have been tested to be comparing like in equal scenarios of recycled content. And then on scenario 2, we're taking 42%, 42.4% recycled content. That this was modeled under the chemical composition during some calculations on the trials from the part of consortium. So we took this as another scenario, number 2, and then finally we wanted to also showcase a best case scenario where we could go all the way up to 90% recycled content and see how these 3 different scenarios showcase. So here, speaking of the steering knuckle, as has been mentioned before, there was a light weighting, and that's also a very important part of the aspect of the reduction in the impact. We can see on the right, we selected 6 of the 16 categories, and we can see some of them have a higher impact because of the impact of the aluminum production. So for example, on acidification or climate change, we can see there's like a higher impact on the overall, but then on exotoxicity of fresh water and human toxicity, we can see there's a decrease in both scenarios on the impact. These are in each one of the different categories. We wanted to showcase the ones that we found more interesting for the study. And going back to the scenarios that I was speaking about, so if we only compare the 30% steel content of recycling with the 42%, we can see there's in a element base of this particular piece, there's an increase of about 25% on the overall impact of the piece. But please bear in mind that this is without the use phase. That is a very important element for this study. So this is just extracting a part of the manufacturing of the piece. And if we increase the recycled content over to 90% and we run the scenarios, we can see there's a decrease in impact of about 9.3%. When that's where we can see starting to see the trade-offs between the comparing different scenarios of recycled content. For the rear frame, we can see, for example, here in the water use, when we increase from the 42 to the 90% recycled content, that there's an increase in that specific category. But if we see the overall impact on the manufacturing without the use phase, we can see that we come from a 56% increase in the impact when only taking into account the 42% recycled content, to a decrease in only of 4% increase in impact when we are taking into account the 90% recycled content. And as I mentioned, these are just at a component level, but the important part is to see the overall picture of how this interacts in the vehicle. So here, for example, if we take into account these 16 impact categories throughout the whole life cycle of the vehicle, and we focus on a climate change category that we know it's one of the important ones, we can see there's a 10% overall reduction on CO2 equivalent impact on the use of the vehicle. We can see on the right that well, the parts that we were speaking about, they're a smaller part of the overall weight of the vehicle. But if we take in, we can see there on this part that the use phase, it's a significant, has a significant contribution in the overall impact assessment of the vehicle. So when taking into account that we're using a 42% recycled content in all of the metal parts of the vehicle, we can lower the total weight of the vehicle to around 954 kilograms. And this is taking a scenario of all of the metallic parts in the vehicle being able to convert from steel to the iron composite master batch. So here is specifically for climate change, where we see a 10% reduction on the impact. And then this is the overall impact in the scenarios with the unique score, right? This is taking into account the 16 categories, normalized and plundered, and this gives us a specific unique score. And in this scenario, we can see that with the 42% recycled content, we have a lower impact, which is better by 15%. And also, this is more evident when we go all the way up to 90% of recycled content, when in the overall result, we have a 20% decrease on the overall impact of our functional unit as a vehicle. So this is very important thing to take into consideration, the use phase and the overall life cycle of the product, and centering that we have some specific impact. When we take the overall picture, we can see a better performance with our case scenario. This also is because we take into account the reduction in weight of the vehicle and also the reduction in the use phase for the consumption of electricity, which is related to the overall weight. So we can project into to get into this 24% increase or better performance for this. And for the life cycle cost of the aspects of the vehicle, we take into account different internal costs and external costs. This right now is just focusing on the external costs. The externalities are based on the polluter's pays principle, which based on the economical value that it has to be got into remediate the environmental impact of a certain component, product or service. Right, so here, if we compare it, we can also see a decrease in the overall aspect of the impact on the environmental externalities expressed in euros. So if we take into account the 42% recycled content scenario, we have a decrease of 10% on the environmental economic impact. And if we go to the best case scenario for about around the 90% recycled content, that showcases a 17% reduction in the environmental impact under the polluter's pays principle. So following the narrative that we spoke about the environmental aspect, going briefly through the economic aspect, and then for the social aspect, let's say the human aspect, our partners in ISQ did all of the risk exposure assessment for the cases, and this assessment was following the harmonized tier approach. This was made into the different stages of the project. As I mentioned, we are taking a very holistic approach with a very with a circular approach about the different, from the formulation to the manufacturing process and then recycling. And the assessment was also reviewing the emissions and the engineered airborne nanoparticles during the value chain. And as I mentioned, they follow the gathering and identifying of exposure scenarios, the monitoring of nanoparticle emissions to analyze the potential worker exposure, and then the earth sampling of the compounds. And the main measuring strategies that ISQ followed were the background measurement and doing the activity measurement and the worker exposure. And with this previous work, they proposed risk exposure assessment with general good practice and recommendations. Just to have a general idea, these are some of the recommendations that ISQ presented on the safety aspect. And for example, in the handling of nanoparticles, the use of low energy for handling or the use of gloves, and in, for example, the validation, the ventilation system and the nanoparticle retention during the handling of the mixture. There are also other recommendations of filter maintenance and regular cleaning of duct layers. And it's also important to mention that these exposure assessments and risk control should be following a case-by-case approach. So this was part of also the human aspect of the circularity approach during a working package to ensure the health and safety. And then finally, through the recyclability, since we have been running different scenarios, the ones that we have showcased here today are just some of the scenarios that we've run. We have calculated the impact of just the FLAMINGo project parts and the conversion of all of the metal parts at different percentages of recycling. And we calculated this graph comparing by volume. So it's 1 kilogram of aluminium, and by volume, to replace that same kilogram of aluminium, it's taking into account 2.69 kilograms of steel. And we compare the different, and this is just about the material. It's very important to focus that on the different the stages of the project. So the components, the numbers that we show are only for the component and then the whole vehicle, and this is only for the material. So here when we take the master batch for the material, we can see that the impact of aluminum environmentally is higher. But calculating the light weight that we can achieve and the density and the environmental impact, at the end, if we have a 96% recycled content of aluminium, that would be similar to the environmental impact of 100% steel recycling content. This takes these two variables into consideration: the reduction in weight and of the overall component that would be needed, and the environmental impact. So yes, as I mentioned, is to reduce the impact we should, the maximum goal is to increase as much as possible the recycled content. And for that also it's very important to manage the quality of the scrap streams to be able to increase the recycled content into this equilibrium point to have a trade-off environmentally for the performance of the material. And thank you very much. That should be all from my side.
Are there any questions? Yeah.
I think I can ask. Okay. Thank you for your presentation. It's very interesting, the process. I would like to know if you consider when you are in the recycled aluminum scenario, you know, during the recycling process of the aluminum, some critical waste is generated, really toxic, and some which generate a lot of contaminants. So I don't know if it's also this considering the recycling materials, I mean the raw critical materials produced during the recycling process of the metals.
Yes, and that's we incorporated all of the feedback from Campacas. So this is the inputs of energy consumption and waste that was from the actual project is going into the model of end of life of the research.
But to point out that there are different problematics related to the waste from the primary production of aluminum, so red mud, etc. And the recycling of aluminum is basically generating just dross, which is an inert oxide-based material. And so from the toxicity point of view, it's completely different.
Okay, so now with this quick talk, I will recap some of the goals and impact made during the FLAMINGo project. Something that you already seen in the previous slides, and something more organized, let's say, in a different way, just to deliver a more consistent overview of the results. So, how to succeed? We knew since the beginning with FLAMINGo that using aluminum and substituting steel is per se winning for lightweighting, because aluminum is basically lighter. And there are already a lot of alloys providing this solution. So for us to succeed was more related to a successful inclusion of nanoparticles in the alloy. It was more also about safety of use of the nanoparticles throughout all their life cycle and manufacturing chain. It should be also acknowledging, assessing the processability of these alloys with different manufacturing methods. Affordability of nanoparticles, because otherwise any good solution could not be actually applied. And also a complete assessment of the recyclability of these materials at the end of the life cycle. And this somehow has been driving also the direction of the project, working on the pre-dispersed and concentrated additives for increasing the dispersibility and inclusion of nanoparticles in the alloy. And on the other hand, we selected the nanoparticles materials in a way that they could be expandable at the end of the path through this manufacturing chain. Expandable and also economically viable. We discarded since the beginning nanoparticle solution like boron carbide or other oxides. So this is more or less the manufacturing chain that we were dealing with in FLAMINGo, from the particle master batch production their inclusion in the alloy, their processing by die casting, extrusion, but also we tested low pressure die casting, high pressure die casting, the use in the vehicle, and then the recycling with the assessment on safety and LCA. So, looking more onto the results from the nanoparticles production. So, we managed to establish a manufacturing procedure for 6 different types of aluminum metal matrix nanocomposite powders. These are based on titanium carbide and silicon carbide. The content of carbide in these master batches ranges between 40 to 30% and up to 60%. And in particular, the titanium carbide is manufactured directly in situ within the aluminum metal matrix, exploiting the fact that titanium reacts with the carbon before aluminum can do it. So the formation of, for example, these nanoparticles is happening directly within the mechanical alloy. So basically, no nanoparticles is actually free to move around, apart from those that are created during the normal procedure of handling materials or cutting materials, or these are called engineered nanoparticles. So since the beginning, we kept this target of €3 per kilogram saved. So it means that for each kilogram we save, for example, from a steel component, we can consider to spend €3 more on the material that is substituted. And this is more or less verified, not on all the combination of processes and particles, but in most of them. So, in the project, we produced 12 different nano additives formulation, 113 kilograms. That corresponds more or less to 3 tons of aluminum metal matrix nanocomposites. Not all of them have been translated into components, but most of them have been used for testing the different technologies as lab and pilot scale. Speaking of which, pilot production trials has been done at the DC casting, extrusion, green sand casting, low pressure die casting, high pressure die casting. So the important thing here, the important results we achieved is that all this has been tested at pilot level. So we had to face many challenges related to the scale of the processes, and in some cases these challenges remain, let's say, remain as a challenge. They have not been all solved. In most of these technologies, we managed to provide some assessment on how these materials can behave, and also how the materials perform after the processes. Collecting different results also for different aluminum series. We tested the 6000 series for the extruded part, and then the 300 series for the casted part. But within those series, more than one alloy were tested with the inclusion of nanoparticles. Of course, these materials, the 6000 series and 3000 series, are commercially available, are developed to perform with very high mechanical properties, strength, and ultimate tensile strength, exploiting a mechanism that is similar to the one that we are using in FLAMINGo, so exploiting the reinforcement by nanoparticles. In the alloy in general, these nanoparticles are generated throughout thermal treatments with the precipitation of nanodispersors. So, by choosing a different alloy composition, we can enhance, or in some cases where we have seen we have hindered the effect of the nanoparticles that we were adding on top of those generated by the alloys. But these results are encouraging in trying to find the best aluminum alloy composition that can profit from the inclusion of nanoparticles alone, which, as we have seen also from the presentation of Christian, are stable throughout all the thermal processes that these materials can face during the lifetime. Of course, in the car, this is not much a problem, but in other applications, this might become a big one. So the topology resulted one of the main effect on the weight component reduction. Of course, when you have a material which is already lightweight, you can increase the lightness by increasing the mechanical performances and acting consequently in reducing the shape, the thickness, and here and there some design strategies. But the topology optimization gives you the possibility to move from 5.3 kilograms down to 2.6 kilograms, and the difference for the nanoparticles addition in here is smaller than the difference that makes the topology optimization itself. So the materials is enabling higher performance in the topology optimization, but the topology optimization itself is making this possible with the counter effect that in order to achieve this kind of geometries, you cannot use any manufacturing process. And for example, the steering knuckle was designed also for low pressure die casting in mind. If I'm not remember wrongly, the mold parts were more than 4 in order to accommodate all the different geometrical features. So we arrived to the test on the vehicle. As we have heard, we have tried the different scenarios on our materials and our how they are applied to the vehicle. The ATX3 was the original vehicle, the commercial one that if you want you can buy Ike in these days. ATX4 is the one that they are finalizing on the design, will be commercially available soon. If we consider substituting the steering knuckles and the rear frame on this ATX4, we can already see a weight reduction that starts accommodating all the increasing weight that this ATX4 is facing due to the increase of safety measures and other components. But of course, we cannot just limit to the 2-3 components that we developed in the project. We should consider a possible ATX5 in which 40% of the steel components currently in the vehicle are substituted with aluminum. In this case, the weight of the vehicle drops below 1,000 kilos, and the effect of the overall weight reduction is much more sensible. But as we have seen, the use of recycled aluminum against steel is of paramount importance. If you are not using completely recycled aluminum, we still having the burden of the primary aluminum costs in terms of environmental and global warming potential effects. By reducing the weight, the effect on the vehicle is multiple, because when you reduce the weight, you can reduce also the battery for if you want to keep the same travel distance, and this means that you are still further reducing the weight of the vehicle. So you can start thinking about changing how to drive the vehicle because it's lighter. But if you start changing also the engine, you are further reducing the overall weight of the vehicle. So basically reaching a new plateau for this kind of segments. And this is true for all the other segments. So we somehow look forward to other possible scenarios in which to apply this material solution. The recycling has been done on the samples, the good ones and the bad ones produced during the project. Two different kind of assessment of the recyclability were possible due to the different kind of nanoparticles in the material. Of course, if you are trying to look for nanoparticles that shouldn't be there at the end, it's difficult to see where is the threshold, the detectability threshold of your instruments. In the case of titanium carbide nanoparticles, you can check for traces of titanium. In the case of silicon carbide, you cannot actually check for silicon content because it's already more or less in the alloy, even after recycling. So two different strategies were used. One was the spectrometry for assessing the titanium presence. The other was just checking the hardness of the material, because we know if there are even a small amount of nanoparticles, the hardness is sensibly changed. And in fact, after 3 steps of recycling, hardness reach a plateau, and we know that the nanoparticle content is below any detectable threshold. Nanoparticles that has to be assessed throughout the entire production and stages of manufacturing. So partners for HQ travel throughout Europe, visiting all of us during the operation of manufacturing the materials, benchmarking them with the background, but also with similar materials that were not containing nanoparticles. And the result at the end is that, of course, each step has a different personal safety equipment required, but in general, those that are already available for the industries for preventing exposure to dust and preventing exposure to smoke are those that are sufficient for dealing with materials containing nanoparticles. By the way, we are talking about containing less than 1%, 2% of nanoparticles. SEA also evidenced that the path that we were following is promising as far as the aluminum content can be increased, the recycled aluminum content can be increased. So this is not only upon us. I mean, there are actually other ways to make this figure to be better. So if it is not aluminum, recycled aluminum, it should be a different way to produce primary aluminum with different batch of sources of electricity, for example. So it's a complex situation for aluminum, but we realize that from an environmental point of view, the possibility to increase the amount of recycled aluminum is of paramount importance in order to make it viable for manufacturing. Otherwise, it sounds odd, but still, it's still the better choice. So, going back to this, so we find different outcomes for the nanoparticles in different alloys and processes. Some cases, these were really improving on the alloy properties. In some other, there was struggling in the introduction of the nanoparticles in the process, or a low increase of performances due to similar nanoparticles produced by the alloy. So on this point, I will not put a complete check mark. But the nanoparticle safety has been tested throughout all the process, and we had no remarks on that. So that was checked to be safe with the current available DPI. It is also processable by current manufacturing methods. The there are some methods that are better than others, and it also relies on how you can actually include the sonication and dispersion of nanoparticles in the melt before the casting. But per se they are processable. And the affordability of nanoparticles is linked with being cheaper titanium carbide and silicon carbide. In particular, the titanium carbide is synthesized in situ. So, and we kept the threshold of €3 per kilogram saved, and we also demonstrated eventually the recyclability without using different protocols than those already applied with aluminum. So if we are putting in the market today an aluminum component with nanoparticles, it can be recycled as any other aluminum component. So in the short term, I already told you which are, you already seen, which are the impacts that can have this technology on a vehicle level. But this is just, let's say, the tip of the iceberg. Going deeper, what we are doing is establishing guidelines for nanoparticle use, recycling, especially when considering aluminum, to provide a wider portfolio of sustainable materials, include also standard regulation, and make them acquainted of this concept of nanoparticles in the materials. That is sometimes not included, and if it is not included, it is seen as an obstacle to material development or material use in the industry. And then the manufacturing guidelines for welding, casting, in particular, of these materials, so that also others can bring this innovation and profit from it. And with this, I finished. Thank you.
Are there any questions from the audience? Yeah.
Thank you for the nice presentation. Actually, I had a question regarding the topology optimization. May I understand this also affecting the entire lifetime? So, I mean, is also the life cycle and the environmental footprint due to the better durability included in the topology optimization, or is it just a property or something that we would like to achieve in terms of performance of the components?
So the design of the components already takes into account the finite element modeling in order to withstand the different forces that the component has to suffer throughout all its lifetime. So the maximum load that it will be facing. And on that side, I can say, okay, the topology optimization is compliant with that. It is not proven the compliancy with fatigue of the components. On that side is a bit more tricky. And apart from that, the overall impact on the environmental improvement is due to the lightweighting effect. So reduced material use since the beginning of the components.
Okay, exactly. Thank you.
Because, sorry, you have the advantage of the, compared to the steel part, you have not the corrosion, yeah? And you have painted or something else? Or
I was just thinking, due to the closure of the presentation where you had the recycling of aluminium, I was thinking whether also the topology optimization can be connected with the easiness of recycling, whether
it's a property of
can
the
be
shape.
correlated.
It's property of the shape of the component. So when you melt it, there's
not affecting
No.
too much.
The less you material you have, less you have recycling material. The main problem at the moment is that the automobile industry haven't much recycling, having not so much steel that they want for recycling material from the industry. Yeah, this was the other part of the world of the industry. Yeah, because no crumble or for steel you need it for recycling. Yeah.
And do they sell out the scrap right now?
Maybe they sell it in Africa as well.
Yeah.
I don't know why. Yeah, this is much more fact maybe.
But probably similar also for aluminum, not all the scrap can be used for making specific alloys. So, and for steel is the same. So not all the scrap can be used for making again the same steel, and this is posing some challenges, which we
I saw
could
3
probably-
cycles.
Hmm?
I saw 3 cycles. The reuse of the specific components. It's quite good, I believe.
Yeah, with just 3 cycles, we are removing nanoparticles, but for separating the elements within an alloy, it's a bit more complicated. So you basically, if you are putting an alloy which contains a certain amount of iron, you basically get that iron out of the recycling process. So that batch can be used only for aluminum alloys with expecting iron in the formulation. You cannot use them for any alloy. An ideal solution would be to have just nanoparticles and aluminum, and when you remove the nanoparticles, you can use the aluminum for all the other alloys. But that was not accepted.
Yes, sure. Thank you.
I think we can pass to the next presentation now. And we can catch up maybe with other questions at the end, because we might have some time. Now we're a little bit back in time. So let's welcome our host, actually Action Innovation, and Vasilis Maris, who will be presenting the innovation opportunities of FLAMINGo.
Yes, hello everyone. My name is Vasilis, as already mentioned. I work for Action Innovation, and today I will present you the innovation opportunities within the FLAMINGo Project. Starting with some words about Axia. Axia Innovation is a consultancy company offering integrated consulting services and specialized in accompanying and supporting companies in all phases of business development and products commercialization. And Axia Innovation is based in Munich. Moving to the next slide. Here you have a quick overview of the topics that we will go through today and within the presentation. We will start with the key innovations, the exploitation potential, moving on to market opportunities and the competition analysis. Starting with key innovations. As already told today, here you have a quick overview of FLAMINGo Project. The FLAMINGo Project is a multidisciplinary project involving a series of technologies from materials, science, chemistry, engineering, simulation, and modeling. Specifically, we use technologies as metal alloying with solid state milling, low pressure die casting and green sand casting, topology optimization, extrusion, welding, non-destructive techniques, and recycling. These activities were supported by IP management, training, SCA and LCCA, standardization, regulation and monitoring, dissemination, communication, and exploitation. Here you also have a quick overview of the innovations that are done within FLAMINGo. We have done the production of aluminum metal matrix nanocomposites additives via solid state mechanical alloying, low pressure die casting for smaller parts, green sand casting for larger parts, and casting of aluminum metal matrix nanocomposite components using ultrasonication and steering systems, the extrusion of cast billets for making profiles for the body frame. The availability assessment of aluminum metal nanocomposites using a range of building technologies, topology optimization for material reduction per part without losing mechanical performance, and the assessment of recyclability of aluminum matrix metal nanocomposites components, and the substitution of steel parts with aluminum ones in EV services, lab validation, and vehicle installation. Moving on to the next slide, the FLAMINGo project will contribute in decreasing the vehicle weight and improve the aluminum's current characteristics. Short lead time with deep integration of combined material, modeling into the value chain of product development and manufacturing. FLAMINGo components will have safety and structural soundness monitored and controlled before the adoption in utility vehicles, electric vehicles, and also aerospace, and the compliance with circularity and zero emission laws. We are very happy to announce that we had our first success stories with topology optimization, and as already mentioned before, with the steering knuckle. Moving on to the market opportunities. Here we have a quick overview of some market researches that we have conducted. For example, in the utility vehicle market, we can see that the market was valued at about 25 billion euros in 2022, and is expected to reach more than 58 billion euros in 2032. The battery electric vehicle market was valued at 720 billion euros almost in 2024, reaching 990 in 2028. And the lightweight material market was valued at 125 billion euros in 2023, and is expected to reach more than 200 billion in 2032. In the recycled aluminum market, the market was valued at 46 billion euros in 2022, and is expected to reach more than 96 billion euros in 2032. And in the automotive chassis market, the market was valued at about 53 billion euros in 2022, and is expected to reach more than 80 billion in 2029. And the steering knuckle market, last but not least, was valued at about 57 billion euros in 2022, and is expected to reach more than 90 in 2029. Moving to the next slide, here you can see the trends in electric cars. Nearly 1 in 5 cars sold in 2023 was electric, so it's a huge number compared to 2022, as it has increased more than 20% from the last year's sales. In the United States, new electric cars registrations totaled 1.4 million in 2023, also increasing by more than 40% compared to 2022. And in Europe, new electric car registrations reached nearly 3.2 million in 2023, also increasing almost by 20% in compared to 2022. Germany has become the third country after China and the United States to record 500,000 new battery electric car registrations in one single year. And 18% of car sales are battery electric, and another 6% plug-in hybrid. Moving on to the next slide, here you can see some opportunities that may arise within the FLAMINGo project. And FLAMINGo can position itself as a crucial player in the rapidly evolving EV market and sustainable materials market. Yes, the first one is the EV market is projected to grow significantly, driven by stricter emissions and regulations. The demand for lighter materials is essential to increase efficiency of electric vehicles. Lightweight aluminum also contributes to reducing the carbon footprint due to reduced fuel consumption. FLAMINGo aligns with global sustainability and climate change policies. And beyond the automotive applications, the innovation in lightweight aluminum can be used also in other sectors such as aerospace, railways, and marine industries. And the growing demand for advanced materials that not only provide weight reduction, but also ensure safety, durability, and cost effectiveness. Moving on to the exploitation potential. We defined the exploitation potential by conducting a SWOT analysis, a pestle analysis, and a pattern landscape analysis. We have summarized a little bit the SWOT analysis, so in order to highlight some points of the analysis. Regarding the strengths of the analysis, we have defined the possibility of replication of the technologies to other sectors, such as aerospace, for example, and the reduced production costs with technology optimization processes. Moving on to the weaknesses, aluminum is more expensive compared to steel. Yet, long term, the cost benefits of aluminum, including weight reduction, fuel efficiency, release, and recyclability, is better. Need for further investments, attract investors with success cases of the project. And moving on to the opportunities, high potential for additional collaborations and demonstrations of FLAMINGo, aluminium metal matrix nanocomposites components to several EVs end users, since EU will implement 30 million EVs by 2030 in the European Union. And moving on to the threats, potential uncertainty of customers and sectoral acceptance, which may be overcome by extensive customer education campaigns and conduct pilot projects, showcasing the benefits of lightweight sustainable aluminum in electric vehicles. Moving to the next slide, we also summarize a bit the pestle analysis. Regarding the political aspect, we defined a new strategy for a climate neutral continent in 2050 towards zero emission. For the economical, we have that aluminum raw material price is more expensive than steel, but as already talked before, we can overcome this with the time. And in social, we have a lack of adequate recharging points in some EU countries, making it a bit more difficult to find a charging station for the car. And for the technological, we have increased demand for lightweight automotive components for fuel efficiency and dynamics. Moving on to environmental, we defined recycling. Aluminium saves more than 90% of the greenhouse gas emission, reduction in CO2 emissions. And regarding the legal, we have stringent government laws and regulations for vehicle emissions. Moving on to the pattern mapping analysis. We did our pattern mapping analysis on a keyword-based methodology, starting to with defining the objectives and identifying technology traits of competitors, moving on to selecting the criteria, conducting an initial search, do the draft report, afterwards we refined the search based on additional feedback that we received. And on the end, we did the detailed analysis of patterns and the comparison with the final concept. And yes, for the FLAMINGo pattern, for the analysis, we did the keyword-based methodology, as already said. The first one was with lightweight metals, then with lightweight metals for the automotive sector. And afterwards, we also included aluminum, and the other one was aluminum composites with nano-reinforced, and aluminum composites nano-reinforced plus automotive sector. And moving to the next page, the first general search, lightweight metals, had 17,657 patent families, with the main SMEs in the market being Honda and Toyota. The main countries were USA, Japan, and China. The main application domain were metal, fiber, ultimate tensile strength, and building construction. And a short notice that we had was that aluminum appears as the seventh technical domain with more patent application, with a total of 826. Moving on to our second search, where we included the lightweight and metal automotive. We had 64 patent families, with the main SNEs here being Tokyo, Tokushu, Denson, and GM Global Tech. And the main countries here were India with 16 and USA with 15, followed by the EPO of 14. The top application domain here were the substructure subunits and insulated cables. And yes, moving to the yes. Thank you very much for your attention. And are there any questions?
From the identified threats that you mentioned, which do you think is the most crucial, especially for a company like ours that is established in Greece and we mainly involved with the recycling process?
For the recycling process or for the ones that I mentioned?
The ones you mentioned, which do you think is the most crucial?
Yeah, the one that we have to extensively educate the customers that are against the electric vehicles and the benefits that we do get from the electric vehicles. And yeah, we can do campaigns and pilot projects as mentioned in order to further promote the electric vehicles so that, yeah, if the persons are more aligned with the electric vehicles, we can overcome this issue easily.
Thank you.
Perfect, thank you. Actually, I believe, especially for I will not focus on the Greek companies, but I believe the problem is a pan-European problem. And it derives from the fact that the last couple of years, as we know, the automotive industry has its main competition against China, and the production is taking a very downward step. And this is especially in Germany with all these big companies producing vehicles. So I agree that it is a threat. However, I believe it can become also an opportunity because, as mentioned previously, with the topology optimization, if someone is able to reduce the aluminium and, in parentheses, can reduce the total cost and the life cycle of the automotive, maybe this can make a shift. However, I'm not very certain because the automotive sector and the sales are dropping.
Short question. In our case, is the aluminium production for electric vehicle is more than for component vehicles. I have research videos that it goes from 80,000 tons to 125,000 tons for electric vehicles. This is mainly casting foundries are more competitive in the market, and they have to be also a good player in the market.
In the European, you mean?
In European, yeah, for electric vehicles.
Christian and Nikos. I will actually return the question to Nikos. I guess that Greece is one of the top producers of aluminium in Europe and across. So the question is, when we're discussing about, also disclosed to Christian, recycling aluminium, how this is affected from transfers from China or vice versa? I think that this is a local industry. I mean, aluminium is taken, is recycled to like factories like Nikos, and they give it back to the production. So I would say that it's affected from China or something similar.
It depends on the production, and some foundries have no full production line at the moment. They produce 50% of the performance, and they produce lower recycled material. Yeah, and they have to buy it from any country or from China. I don't think they buy it from China. They use it by themselves. And this compatibility depends on a lack of scrap and aluminium, secondary aluminium for the production. Yeah.
Okay.
Because you BMW also, I think he uses 80% recycled material. They have to be used for the European Union. You have to be 80% recycled material for casting parts or more. Yeah. But you have to be economical.
I don't know what happens in the industry in Europe and China. What I know is that the needs are becoming bigger and bigger, and the orders are becoming bigger and bigger every year. So yes, so don't know if there is a real affection.
You're right.
Thank you very much, Vasilis.
Moving to the next presentation of today, we have the presentation from Excelsis with the outreach and success cases of FLAMINGo from Government Consortium.
Thank you, Vasilis. Hello again, everyone. So I will start with some success cases. The outline of this presentation will focus on different communication tools and channels that we use, dissemination actions. We will present some of the awards that we have one award that we have been awarded already, and one application, and then some best practices as a summary of the activities we have been running over the last almost 4 years. Before I start the focus on FLAMINGo, I will give a very short presentation of the company. Excelsis is an engineering consulting company located in Athens, Greece, and our field of expertise spans across innovation management, IPR management, technology transfer services, and business development, as well as engineering consulting, patent mapping. We are organizing every year events and running marketing campaigns, as well as design of brand identity and video creation. Our fields of expertise cover business, the energy sector, engineering sector, waste management and circularity aspects, as well as materials and nanotechnology sectors. Making an overview and summarizing some of our achievements, we have a network of more than 500 companies and institutions. We're organizing several events, quite successfully every year, organizing 4 events every year with attendance up to 400 people. We are very active in our social media channels with a reach more than 600,000. We are also having expertise on circular value chain assessments for value chain optimization and circularity assessments. More than 10 cases are already run in different sectors and value chains, and we are also part of different spin-offs. Currently, we are running 3 entity establishments. So back the focus on FLAMINGo, and starting with the communication tools. As you know, we have this unique identity with a FLAMINGo bird designed early on in the project. And we are always using these uniform colors and design and uniform templates to showcase all our results and summarize our achievements. We are using different infographics to present our messages in an eye-catchy way and in order to be short and demonstrative. So in different presentations on our social media, on our website, and in different printed concepts. we have developed a lot of videos and we are posting them on the FLAMINGo YouTube channel. So we have 9 videos overall, starting with an overview of FLAMINGo, different workshop videos from different meetings, the fairs that we attend, some footage from the labs and the pilot lines, and summaries from the clustering activities. Our latest video was offered by Auke, which is the demo video of the parts that were developed. You can check them all on YouTube. Continuing with the social media platforms of FLAMINGo, there we're sharing updates on a weekly basis, sometimes more than one post every week, in order to engage our audience and build the FLAMINGo community and enhance, of course, our brand presence. Namely, we have our accounts on LinkedIn, Facebook, and the X platform. Overall, the last 4 years, we have counted more than 170 posts. And on LinkedIn, we have a quite big community with more than 1,000 followers and more than 160,000 post impressions. Also on Facebook, we have almost 2,000 reach. And on the X platform, we're counting more than 600 followers with more than 32,000 post impressions and counting. Our website now is one of our very powerful communication tools. There we collect all our information, we engage with our audience, we try to design concepts that enhance the visibility of the project, and we're sharing our updates in dedicated tabs and the major events that our consortium attends. Here I want to share the video, just a moment. Here, this is the overview of our website with the general overview. On our homepage, we're announcing important events like the one that we are here, our fact sheet from the LIDDs cluster, the different technologies that we are dealing with, as well as the new news section that we update periodically. Overall, since the beginning of the project, we have this very interesting reach of a million event count, which is linked also with the award that I will present in the next slide, which was awarded to our website design and structure. Over the last 4 years, we are counting 166,000 users and more than 400,000 views on the FLAMINGo website. So coming now to the award, we had the honor to gain the award at the EU READ 2022, where this is a big event organized in Mechelen in Belgium with 6 categories and 18 contestants. We were the winners of the Laurels category for the FLAMINGo website. And the award was a sponsored campaign of 5,000 euros, where we used these campaigns to promote the FLAMINGo website, as well as the LCA workshop that was running at that time, and promoted through the X platform and the LinkedIn account of FLAMINGo. So this linked to the high reach and engagement on our both social media and the website. Currently, as we seek for different opportunities to disseminate the project, Alana from Global Factor had this nice idea to apply for the Konama award. So this application was concluded the last week, and in general, this award has 2 different prizes. One is a jury prize, and one is the public award. And the overall concept behind this award is the eco-design of products, services, or business models with the necessary considerations to reduce the environmental impact. So we're under this process and we will keep you updated on this. Moving now to dissemination. Dissemination is very important for us as well, as we identify different messages and we try to reach different audiences, not just the wider public, but also scientists, stakeholders, etc. So we have different pathways and we are consistent in reaching them. First of all, I will refer to the dissemination materials that we have been developing and our consortium is sharing with their networks in different events and occasions that they attend to. There are different flyers, roll-ups, and posters, different concepts and different versions of them. We are updating them whenever needed. Different agendas and fact sheets that we are developing. I want to point out this fact sheet for the Enlighten, this cluster, which was developed with the collaboration of the Horizon Results Booster, as all projects gave input on developing these materials. Also, regarding expo materials, when we're attending an expo, we are sharing at least 6 concepts per event. As in the case of the GATS Expo, the Global Automotive Components Suppliers Expo, which took place last year on December in Stuttgart, where we had different banners for the booth. All the setup of the booth was designed by us. Different stands or the agenda or tags and the photo frame. Moving now to our workshops where we are organizing in-person and online workshops and training sessions. Up to now, we had 6 different workshop organizations. I'm highlighting 4 of them. It was the Salerno workshop early on, late 2023. The EU Green Week, where we summarized the essential skills for lightweight aluminium. Then it was the LCA workshop, which was organized along with the MIDV's cluster, as mentioned before. And the workshop from AWF at their 59th General Assembly. We have also been running some citizen science events, and in the case of FLAMINGo, we have visited a high school. It was a high school activity with more than 50 students and teachers, where we presented the FLAMINGo concept in Greek language, and also we made a press release on a local newspaper in Greece about this event. I will now summarize some of the trainings. This is an activity that is led by AWF with the participation of the whole consortium. So we'll start with MBN that gave training about additive production, Constellium about the fundamentals of aluminum extrusion, ISQ about nanomaterial safety, and concluding with Axia Innovation about innovation management. Global Factor had an online event about the LCA LCC, Kambakas about the aluminum recycling, and the final one about the lightweight aluminum manufacturing technologies. Now moving to our events. As I mentioned, our consortium is very active in attending different events on site and online, of course. So here I'm summarizing some of them. Overall, they were 15 over the last years, excluding the fairs that I will present on the next slide. So it was the IAA Mobility, the Astria event that was where Ogi. Are you the organizers as well?
Yes, yes.
Yes, okay. And the Austrian Foundry Congress again, TRA 2022, where Lamberto was there, along with the cluster, and the Nano Commons conference. Moving now to our fairs, as I said, the consortium is very active again here, building different booths counting 10 fairs over the last years. One of them was, of course, the one in Graz that we had with the Enlightened cluster. Speaking of which, let's present the Enlightened cluster as we have been speaking about this, and Lisa will share a nice presentation at the end summarizing the success cases and some sum up of the different projects. Just to mention that the other projects have already finalized their developments, and we are the last ones still running. So it's the FLAMINGo project focusing on advanced lightweight materials and processes for the eco-design of the electric vehicles. Is the fatigue for light, fatigue modeling, and fast testing methodologies to optimize part design and to boost lightweight materials deployment, and with a special focus on the chassis parts. It's a LEVIS project for advanced lightweight materials for sustainable electrical vehicles by integration of eco-design and circular economy strategies. And finally, it's a Revolution project supporting the electric vehicle revolution through maximizing EV range and end-of-life vehicle recovery. Apart from the Enlightened cluster, however, we're very happy to be collaborating with different initiatives, all focusing on green mobility and lightweight materials for automotive and beyond, of course. As you will see here, we have a Colabat cluster, which is a cluster on electric battery systems, being part of Albatros, Helios, Liberty, and Marvel projects. The Mimosa project, which focuses on multi-material airframes this time. It's the only project that is not focusing on automotive, but it's the same concept like developing the 3D joints between the metals and the carbon fiber composites. We will have, for all these projects, actually I didn't mention that they are invited projects for this event today, and we're very happy for this. So we will have brief presentations from all of them right after my presentation. So I will just present the titles, and you will take over then to present in detail. So then it's FlexPress, flexible and hybrid manufacturing of green aluminum to produce tailor-adapted crash-tolerant structures. Then it's the Zebra project, zero emission electric vehicles enabled by harmonized circularity. Then it's the Multum project, multi-material additive manufacturing for lightweight and thermal management. And then two projects that couldn't attend, this is why they're not on the agenda, but we have been collaborating in the past and attending different events together, is the Salium project, novel concepts for safer, lighter, circular, and smarter vehicle structure design. And then it's a lemma for the substitution of critical raw materials on aluminum alloys for electric vehicles. As mentioned, we are organizing them common workshops. With some of them, we have both participation in common or different events, webinars, etc., as well as we have social media engagement among us. And with Salim, we also have an agreement for mutual dissemination efforts. Now, regarding our publications, we have been publishing our work openly. We have 3 scientific papers and book chapters. They're also available on Zenodo, along with the different open access reports that we share there. We have newsletters that we develop yearly. So currently we have 3 available issues, and 1 more will come at the end of the project. And then we had 19 press releases presenting different key events or achievements along those years. This is my last slide, where I will summarize some best practices. There are plenty more, but I just summarized 5 of them. First of all, our sponsored campaigns were very, very effective. Over the years, we have seen over 11,000 post engagements with our sponsored campaigns. We have reached more than 6,000 views on our videos, etc. So this was a tool that we have been using from half of the project, let's say. Then regarding clustering, we had planned regular meetings with our cluster, and this was very effective also because communication every month is very important to set new goals and think of how we're going to move forward with the different projects and our organization of different events. We're always mapping our activities to keep track of them, and the consortium is very, very helpful on this because they're collecting and putting together all these activities. And then regarding our events, we're also always asked our consortium to share pictures on the spot so we can share the dissemination corners, the different presentations. What would be even better here is to share videos which would highlight more and engage more people in future posts. So this is a suggestion apart from a best practice. And then regarding opportunities, as I mentioned, we grab any opportunity to boost our project, to showcase what we have done. This is why we are applying now for this award. And it was, we hope it will be as successful as the one about the website. So just an overview of what we have reached so far. Different events, as I mentioned, this is a summary final slide. More than, organizing 2 conferences and 3 workshops, participation in 15 conferences and 3 workshops. I already mentioned the press releases and the newsletters, 10 expos with a booth from different partners. 7 activities of them were jointly organized with other projects, highlighting our clustering efforts, and 3 open access publications. With this, I want to thank you, and I have concluded the presentation. I can take questions if you like. So now that we concluded, who will go first? So I want to give the floor to Christian Kurspur from Virtual Vehicle, presenting the FlexCrash project, and especially a presentation titled FlexCrash: New Generation of Crash-Tolerant Crash Structures.
Exactly. Thank
Thank
you very
you
much.
for being here.
Thank you for the opportunity to present our project, FlexCrash. So, as said here, we are working on the new generation of crash-tolerant structures. To give you a short overview of our project, we are actually in the middle of our project, so we have 4 years of project running time. We have about 10 partners from 5 different countries and about 4 million euros project budget. We are one of 3 projects funded in this cluster 5 call, testing safe lightweight vehicles. So the Salient project is one of our sister projects, and also the project ROSI, which we are coordinating in Austria for the virtual vehicle. So I'm here for the FlexCrash project, so I also have some information if needed from Salient and from the ROSI project. What does our consortium look like? We are, I think, quite a balanced project consortium from research centers, project coordinator EuroCAT. We have the FLAMINGo EVS and ourselves, the Virtual Vehicle Research Center. From the university side, we have the University of Munich and the IMC Krems in Austria. Industry side, Gemma Technology, and also hooked up with Stellantis from Italy. And on the industry side, the Geston and Aerobase from Sweden. And we have also included the standardized body, the UNE in Madrid, who is responsible for our legislative and patent work that we are doing in FlexCrash. So, what's the motivation and the vision of FlexCrash project? The goal is to have vehicle lightweighted as much as possible. The problem is the passenger safety on the other side, and also the sustainability of the used materials and the structures. So these 3 points do not fit well together. So when you're thinking of standard manufacturing processes, when you're going lightweighting in the vehicle body, you're losing passenger safety. You have to do that with active systems and other systems and so on. And you also have the problem with sustainability. So when you're thinking of lightweighting, when you go into fiber reinforced plastics, for example, then you have the problem with the sustainability on the other hand. So what's our way to deal with that? We want to try to focus on 5 pillars in our project. So we have 4 technological pillars and 1 legislative pillar in the project. The first pillar is our manufacturing and our manufacturing technologies. So we want to use 3 different manufacturing technologies, from extrusion technology, from high pressure die casting, and also from 3D printing, from additive manufacturing. So this looks like this. We have our base materials produced by extrusion or by high pressure die casting, and we are adding there some so-called AVFFs, so added value functional features with 3D printing, also called the LMD process from FLAMINGo. So with this technology, we can adapt our passive structure, our passive crash structure, to the needed purpose from the different load cases and crash scenarios, from actual loading scenarios and also from future crash scenarios, which will come a little bit later. So this is one of the pillars, of the technological pillars, is the manufacturing part. The second pillar is the design of such new crash tolerant structures. We also mentioned in our proposal that we will use not only the passive side of our crash structure, we want also try to include some kind of active system in our loading pad, so to enhance or to be more precise for different load cases, especially in the future. Actually, we have these legislative regulations which a car manufacturer has to fulfill, and also this Euro NCAP regulations, let's say it that way, so these customer related requirements. And this can be done with this passive structure, as found normally in every car nowadays. But when it comes to these extended crash scenarios, for future crash scenarios, future crash situations with higher ADAS system, with better ADAS system, these crash scenarios will change in certain ways. We have wider crash angles, we have lower or less impact speeds in some scenarios, and to fulfill these, to protect the passengers and the occupants as much as possible, our target is to integrate the active system. Here the active system is designed with hydraulic actuators. We need therefore some sensor systems and so on. A little bit of problem, I cannot go in deep in this active system because we are actually working on a patent with Stellantis on this topic. So this active system will help us to prevent these future crash scenarios. The loading situation, or to reduce the loading situation on the passengers, on the occupants, and on the occupant car, for example. And the combination of these passive and an active system is for us one of the solutions to fulfill a wider growth of different crash scenarios in the future. In the end, it should be an optimal deceleration path, for example, for the passenger in the combination of these two systems. The third pillar is also coming from Salema, as mentioned before. We are going to have an advanced testing and crash toughness and fracture fatigue of these recycled aluminium, what we are going to use. So what we need for especially our work on the virtual side, on the validation of these material cards and these simulation methodologies we are using, we need a good and validated material properties. So we need to know what the material properties are, what the characterizations are, not only in the Young's modulus and fracture toughness. It also has to be these the breaking behavior, the damage behavior, and also localizations of, especially with these high pressure die casting materials, we have some local effects that we have to visualize, and we have to validate in our material and simulation methodologies. And therefore, we are doing a lot of testing work on coupon level and also on component level to understand the material and to create and develop and validate it as material card for a good forecast probability. The fourth pillar is the crash simulation itself. So we have to show how we are going to deal with the production process, how we integrate that in our design phase, in our validation process, and in our crash simulations, and in our predictability of our methodologies. Therefore, we are going to use from the company Gestamp the GLab virtual model as a demonstrator. You can see here on the left side, this is this classical front-end system with welded sheet metals, front bumper, these rail systems, these crash systems, and on the right side, the integration of the Salema part. So we are going to use the Salema part as a baseline, extruded parts in the front crash system. And as some of you know, the Salema part is not designed for crash purpose, so it is a quite heavy and stiff part. So the first step was to redesign a little bit the Salema part. So this has to be done with topology optimization and crash simulation on the right-hand side. So we have to rethink a little bit or redesign a little bit the Salema part for our crash purpose. So this was the first try. In the first step, we can reduce the weight. On the second step, we can optimize the crash bolts for the passengers. And this was the first tryout. And in this system, in this Salema part on the right side, we are actually working on this active system to integrate in these Salema parts and the active part to optimize further the weight and the crash pulse for the passengers. That brings me to the last pillar, this legislation pillar, the identification of the future safety needs. When these ADAS systems or autonomous driving cars are becoming more and more popular, the crash situation will change in certain ways. And for that, we have these mobility safety needs, these simulation methodologies where we can create crash scenarios with different boundary conditions. And for that, we have identified 3 different crucial crashes for the future. This is this on the right-hand side, nearly 90% crash, this 110-degree crash, and at least this 150-degree, which are the most crucial ones for our purpose and what we think in the future will be happening more and more. And these left turn across paths with opposite direction. You can see on that side is mirrored from this crash scenario here in the upper left corner. This is the most crucial one, and this is the one we are actually focused on for our validation of the crash system. So where are we actually now? We are, as said before, we are in month 25 actually, so halfway through the project. We have done our work on the crash information and improving crash simulation buildings, and we have this crash scenario generator where we can generate different scenarios, different loading scenarios for whatever we think of. And now actually we are working on the material and the manufacturing solutions, and parallel on the validation and the verification of our simulation methods. Yeah, I think we are on a good way. We can show in different ways that we can lightweight the front-end system with different manufacturing technologies. We can integrate recycled aluminum in these components, and in the end we can validate all of these methodologies, technologies and so on to show how we can lightweight even more on different components all over the car, future body and light. So thanks for your attention. Are there any questions?
Are there any questions from the audience? Yeah. Thank you for the nice presentation. It was actually a multi-component presentation with a lot of different things in order to achieve, as far as I understood, one of the scope is to have this crash simulation results and to improve the life cycle of the vehicle, or
to improve the life cycle is what we want to achieve is that we can integrate these recycled aluminums. So not the life cycle at all. Life cycle will go better if we reduce the weight. So as discussed before in several presentations. So the goal is to integrate this recycled aluminum was developed in Salema. And with the Salema alloy, we are going to integrate different manufacturing technologies.
Okay, sorry, I was not aware about this collaboration with Salema. I guess is another project.
It's another project. It was mentioned before on this overview. Eurocup was also project coordinator of the Salema, when I'm not wrong. But was also included in the Salema consortium. And from there we get these parts and also the overview.
Okay, actually this would have been my question more or less, starting with pillar 1, because I was not very clear about pillar 1, because I saw in the beginning you are using an additive manufacturing method in order to produce the components. So I was not clear about the materials used there. And my question would have been, if finally the use of certain materials that you are using, is it affecting, and to which percentage is it affecting this crash simulations? This would have been my question.
I don't think that we can say how many percent we are affecting the simulation. It affects the simulation because it is a little bit, it's comparable to classic prime aluminum. But the material properties differ a little bit, especially the scattering of the material. For example, my fracture, elongation and fracture, for example, is quite different to a prime aluminum. And for the crash simulation, this fracture and this damage is our main use. We use that for energy absorption. So we have to destroy components to absorb energy, and for that we have to clarify, or we have to test before a lot of different coupon level tests from the new used materials. This is the main point from the usage of the different materials, And the second point was before this manufacturing technology. So we are also trying to adapt to combine different manufacturing technologies together. So we are using these high pressure die casting, for example, and add on features with these additive manufacturing technology, and also on the extruded parts. So we try to be as thin as possible with the extruded part, for example, and add on with additive manufacturing, different patterns and so on, to be as stiff as possible in the end, but lighter than before.
Okay, clear enough, thank you. And one final question, and it came just in mind. Can you also integrate in your crash test calculations or whatever, because I'm not an expert to all of this, can you integrate parameters of recycling cycles? Or is it something?
Not directly.
No.
You typically use that for in LCA analysis or in these analysis of this for the crash simulation. We do not use that. So we get the different material properties, but we do not care about how these are. Yeah, exactly.
Okay, thank you.
One more question?
Okay. Thank you for the nice presentation. I think you mentioned at some point that so with the recycled material, of course, there's inherently some difference in the same elongation pattern. I guess perhaps more specifically for forwarding deformations when you form the material. Is this when you recycle, of course, there's going to be a difference in composition. Is this the reason why, or is there something inherently related to the recycling that leads to this difference in folding characteristics and deformation?
That's a good question, but I'm more the simulation guy. I'm sorry for that I cannot answer this question. Why is it that the recycled aluminium material is different to the prime aluminium? What we can see here, just a few slides. We got this from Eurocat and our colleagues from Sweden. What we see here, for example, when we have this prime aluminium characterization and a little bit less, we have the secondary aluminium. And these difference we have to also include it in our simulation methodologies.
You account for it.
Yes.
Okay.
We have to deal with it in the topology optimization and also in the crash simulation.
Okay.
Because these influences our crash behavior a lot. And that's the main point, especially in the characterization. We took these data and go in our simulation models and try to be as good as possible, as thin as possible, and to
Okay, thank you.
Welcome.
Just if I could also make a question, picking up on the simulation, since you're an expert, as you said. Well, the question would be how these nice simulations that you showed would be validated with real crash tests.
So typically we are starting on coupon level. So we are simulating tensile tests, three-point bending tests, and so on. Then we are going on a component level. So we have, for example, the Salema part, and we will crash only these parts. We have to validate on this level. And in the end, we are going to crash the full front end. So we are going to crash at least 3 full of these front end systems with just a passive crash system. The active crash system, we have to look on if it's possible to integrate it in the crash facility, because it's a little bit tricky, let's say it that way. But we are going up to the full front end. So what you can see in the direction on the right hand side. So these front end systems will be crashed at least 3 times at Stellantis test facilities, and not the full vehicle. So this full vehicle, what you see on the left top side is only a virtual vehicle. It's not produced or manufactured, and we are just going for these subsystems.
But it will be a real crash test within the project.
Within the project.
Thank you.
I try to be fast. So, I am Giorgio De Pasquale from Politecnico di Torino in Italy. I'm the coordinator of MIMOSA project. That is a project about multi-material airframes based on 3D joints between additive manufacturing metals and carbon fiber composites. Few words to introduce the consortium. We, as Politecnico di Torino, we are the coordinator of this consortium, which is composed by a big aircraft maker, Leonardo Aerostructures, this Italian company, and another big company for certification, TÜV SÜD. And then we have another research center, Johann Neumann Research in Austria. Then we have V-Plus, that is a company specialized in composite fabrication in Slovenia. Fenice is an Italian company working on recycling of metal for producing powder for additive manufacturing. GBP is from Spain. They are also specialized in recycling materials. Okay, this is the consortium. Our project goal is to develop a new concept of joint for metals and composite. You know that in aeronautics, but also in many other fields, we have a lot of applications of these two materials, and normally they are joined through rivets or adhesives. This causes a lot of efforts in the manufacturing. In aeronautics, we have roughly 12-13 steps to create a certified joint between these two materials. So we are looking for a new strategy for to obtain this joint. And it's not only a matter of complexity of the manufacturing process, but it's also a problem of stress concentration, because when you put a rivet, you need to drill a hole that causes stress, local stress, and this reduces the reliability of the structure. Then you have the weight of the rivets. On one traditional aircraft, we have about 100 kilograms of rivets. That is a lot. And of course, pollution, chemical treatments of surfaces, and so on. So eliminate the rivets was the goal. And after this innovation, we could also improve other sectors like energy generators, like automotive, racing cars, and bioengineering fields, sports facilities, and other kind of applications. Here is a typical structure of a primary flight structure. You have a metal part inside, ribs, parts, and so on, and a composite skin. These parts are connected through rivets. And what we are doing in the MIMOSA project is to change the concept of the joining process. And basically, we process the metal part by applying a texture on the top using additive manufacturing methods. And we create some spatial structures in the mesoscale that are able to engage mechanically the fibers of the composite part and obtain the mechanical connection without using external elements. This is the idea. Of course, we need to optimize the two processes that normally are independent, the additive manufacturing of metals and the composite lamination, and also to provide a suitable interface by applying a atmospheric plasma coating that has the function to improve the wettability for receiving the polymer matrix of the composites, and also to prevent the galvanic corrosion between the two materials. Then we have a lot of activities about the designing of this surface that is an engineered surface. So we have small features that must be optimized in terms of shape. That also means technological rules, so minimum dimensions, connection radius, and tolerances of the additive process, but also means reliability, especially about static and fatigue loads, so optimization of the density of the material, the reduction of porosity, and all other possible issues that may cause lifetime reduction. Of course, we also have an autoclave treatment to polymerize the composite that is also applied on the metal part. The autoclave treatment is done after the coupling, so the metal part also receives the autoclave pressure and temperature that modifies the thermal treatment of the additive manufacturing process that is normally applied. And we have also to account for this. The two processes involved are basically the additive manufacturing of metal, that is a traditional process for the deposition, that is laser-based, powder-based process, and the laser power source. But the heat treatment is customized because we have also to account for the autoclave post-process. The second part of the process is the composite lamination in autoclave. And here is a real innovative process because we have to modify the coupling of the two materials by introducing new manual operations in the project that are designed to be standardized and industrialized after this first step. Another big part of the project is the recycling of the materials, because we want to provide a cyclic life of this technology. And so we are planning also the reuse of the metal part and composite part after tape separation, after the end of the service. The metal part is, in particular, is the innovation part for recycling, because through atomization process, we regenerate a secondary raw material that is basically aluminum powder that can be reused for a new additive manufacturing process. And for the composite, the recycling is more traditional because basically it's pelletization, so reduction in small parts to create some particles to be used as filling materials for composite, for polymers fabrication. We have a big part about the designing, the structural designing, and the optimization of shapes, dimensions, calculation of load distributions, multi-physical coupling, because we have primary flight structures interacting with the airflow that generates structural loads that are the input specifications to dimension our joints. I cannot put some, we have some prototypes to show, but the video are not so optimized to show, so you have to wait a while for that. Our website, they will be published soon. And to conclude, the project has some main goals about the future exploitation in terms of supply, provide a new solution for hybrid propulsion to reduce the weight of structures, reduction of consumption in flight, thanks to lighter structures, reduction of pollution in terms of chemicals and paints that normally are needed to prepare the surfaces before the coupling, that here can be avoided. This new concept allows also to couple together the two technologies in the same plant. So you do not need to move materials, semi-finished materials from one plant to another. You don't need to move composite laminates or metal parts. You can produce both on the same line, and this also reduces pollution for transportation of materials. Then the reuse of materials also opens to new markets opportunities for that companies that want to recycle this kind of materials. In general, we are able to provide a simplification of the process of this manufacturing of aerostructures, not only aerostructures, of course, but this is the topic of the project. And we also have to produce a detailed business plan for the next industrialization of this technology. And Leonardo is doing this on its own production, and they estimated a reduction of process time to build one single joint of about 65%, of the cost about 15%, and the energetic consumption of 60%. And we are working on this business plan that is really industrially driven because it's applied on real production facilities, so it's quite reliable. This is just a very fast description. Here are the contacts, the websites, and my emails in case of additional questions or even suggestions or proposals to cooperate or to extend this project to other applications. We are open, of course, to discuss with everybody. Thank you.
Thank you very much for the presentation. Are there any questions?
It's okay.
It's only for the...
Okay. So, thank you for your presentation.
No difficult questions, please.
No, very easy. I don't know if I missed it, but regarding the low carbon fiber composite, which one is the polymer matrix?
Oh, this is a difficult question
Okay.
for me, but I can say that we used industrial composites that are already certified for aeronautics,
okay,
because this is a requirement. We are exploring some new composite with some nanofibers. I am sure that we have much more details on this in the consortium.
Yeah,
and I will provide you more details.
We can discuss later then.
Yeah, you can just send me a reminder by email and I send you a lot of pages of this. Sorry, but I'm the coordinator, but I don't know why I'm not the expert of everything. So sometimes I don't know.
Thank you.
Thank you.
Thank you for the nice presentation. Actually, my question might be a little bit connected with the previous one, but not in the terms of the materials used. I'm from AXA Innovation, and we are working in the business models of FLAMINGo projects. And because also you closed very nice your presentation regarding this, I was just wondering to see whether you work also on the circularity of this business model. Will it be a circular business model? And my question comes from the multi-material use, because traditionally right now there are not a lot of recycling options for new multi-materials that especially can be reused and added again in the value chain.
Yes, it's a pretty new approach, as you say, because there are some companies that are starting to exploit opportunities for the recycling. But generally they are not connected to one specific application. They are multi-purpose, of course, because they need to work. And so when you go to a specific application, it's hard to find commercial data or simply the price, the selling price of recycled powder or this or that. I think my feeling is that at now the secondary raw material, and especially the powder, the recycled powder, has a market price that is still quite higher than the traditional powder, and so this business is strictly linked to the public incentivization that you have for using recycled. You know that you can have some taxation reduction if you use some powder recycled or not. This is now pushing this market. Of course, it cannot work forever because the market has to say if the technology is able to reduce the price cost of this or not. We are waiting for this. So we are in this very first transition period, and it's we have not, as you can say, so we don't have certain rules, benchmarks. They are competing each other, these startups, especially. So we will see, basically.
Actually, I'm not very aware about these multi-materials used, and I was thinking more or less about the recycling by its own and the capex and whether all these costs, because it requires a lot of research also in the recycling process, I guess. So integrating this into the cycle, whether this can be estimated already or it's something that...
No, we can estimate the specific recycling because atomization, we are using atomization, is a stable process. You can calculate the cost of the equipment, the cost of the process, okay. But you also have some activity for the separation of the materials, for the treatments and of the other side of the joint. And all of this is not stabilized, it's not consolidated.
This is why I mentioned it also. It probably has to do also with the material polymers.
But it's one of the goals of the project to highlight this.
Okay, thank you.
You're welcome.
I think one last question before we move to the next
Also,
presentation.
I guess that in the consortium you have in your hand will be Voya from your hand. No, it's working.
Sorry,
Voya from your hand.
Yes.
He's working.
Yes.
Give my regards, we will talk later. So, I guess that the competitor technology are wet methods for joining, where we have a pre-treatment of the surface of the metal, etc. This plasma treatment can compete to the productivity of these methods. I mean, I can understand plasma treatment is a good process for small areas, unique parts. When it comes to mass production, can it really compete the wet methods?
I think the bottleneck is also additive manufacturing here, not only the plasma. So it's good because they have the same limitations. That means that the designer should limit the application to specific dimensions and components. That is good because it does not exist a technology for everything. The important thing is to know the limits and to know the application field. But I agree, there are some limitations, but we are lucky because they are almost the same on the additive manufacturing of metals.
Thank you.
Moving on to the next presentation for today, from the FLAMINGo Project from Smart House Now. With the title Multi-Material Additive Manufacturing for Lightweight and Thermal Management, a New European Horizon in Metal Polymer Components.
Thank you very much for inviting the FLAMINGo Project. Congratulations for the nice results to FLAMINGo Project and for finalizing successfully. I'm presenting Munden. It's the kind of a sister project of Mimosa, but there's differences that I'm going to highlight. I will try to go very fast, but I prepare aluminum technical part because I knew that some people maybe would be interesting. So I will pass the Munden information quite fast and go to the aluminum technical content. So as he said, my name is Marta Alvarez, and I'm Advanced Material Coordinator of TETEMEN. I made my PhD in severe plastic deformation in aluminum and magnesium alloys, so hopefully you will enjoy the presentation. So the needs from Europe were at the beginning the lightweighting of complex shapes components, the improved heat dissipation of lightweight structures, and also the reduction of the lead times. As we mentioned today, we are in a competition with China and the United States. I'm talking about the European industry, so we have to improve our processes. So in this sense, the vision of the Munden project is to use the advantages of the additive manufacturing for metals and carbon fiber composites to develop and validate new reliable processes related with additive manufacturing, as I said, to generate a new metal polymer multi-materials with the structural and cooling functionalities and also with a cost-effective approach. Okay, this is quite obvious, but I would like to mention it. The multi-material solution would mix the aluminum and the carbon fiber composites. On one side, we know that aluminum is a lightweight metal alloy and also is a good heat dissipation and mechanical property material. And also on the other side, we have the carbon fiber composite with this high strength and replacing more and more metals in the way of reduce the weight of the components. So, how it is structured? So we have work packages related with the materials development in metal polymer reinforced side, and also the work packages related with the use cases, because we have 3 real use cases from the transport sector. We have developed different material in the first year. Now we are in the second year developing the design, the topological optimization and the simulations. And then we have to implement all this research in the use cases. So on the metal side, I don't know if, yeah. We have mainly 2 technologies, DED with wire, also called LMD wire, and DED powder in settlement, and also we have the partner Prima additive on the side of powders. And also we are using laser powder perfusion for some of the developments because the DED processes with aluminum is quite tricky. So sometimes we need also to use a more conventional additive manufacturing technology for aluminum. The alloys are aluminum silicon magnesium, the 7 magnesium, and also an alloy 5356. On the composite side, we are using material extrusion with filaments and also material extrusion with continuous fibers with the partner list and also TNO in Netherlands. And here you can see some of the solutions that we are generating with continuous carbon fiber. We are using as a polymer matrix the PA6 and also the PEC material. One of the interesting development that we perform with additive manufacturing is to create the PEC material with a continuous carbon fiber. This is quite new and is by the moment really successful. And also the other group of technologies related with the welding technologies for put together in the component the metal and polymer, reinforced polymer, is electron beam welding performing Fraunhofer IPK, and also the robotic friction steel welding in Ferment. Well, regarding the use cases, we have the battery casing for an electrical vehicle, and also the motor housing for an electrical motor for a drone. These both use cases from 80 Composites and Knight Electric, both SMEs, are being developed. The idea is at the end to replace a complete casing made by 100% of aluminum, replace it, reducing the weight by 50% into a solution like this one, in which you can see the blue part is going to be made by the continuous carbon fiber composite, and the rest of the frame of the structure is going to be made by aluminum, because as I'm going to mention, we need the heat dissipation properties in these components, so it cannot be made completely by the composite. Okay, so the outputs, we need to reduce the weight by 50%, which is ambitious. Decrease the lead time by 25%, and we propose to increase the performance by 30%, and I think this point is going to be the most challenging, because nowadays the 100% aluminum is already really optimized, so we will see if we can achieve that. Okay, very fast about the partners, as I mentioned some of them. We are finishing the project next year at the end of 2025, and the total budget for the project is 4.5 million. It's very similar to the FLAMINGo project, as I saw, and also the number of the partners is similar, so hopefully we can collaborate. some pictures of the meetings that we already celebrate, the technical meetings. And yeah, and to finalize this modern part, we are really involved and really active in the advanced materials initiatives that are arising right now. So as you may know, cluster, which is gonna be called AM4EU partnership, a partnership, is starting right now. So we are a partner in this initiative. So hopefully we will see each other within this partnership soon. And also we are developing some standardization activities, also collaboration with Stanford.U and so on. Okay. Focusing on the aluminum-related technical part of the project, I will comment very briefly the works performed in FETEMET within the Munich project. First, I will present the entity very fast. We are a technology center. Mainly our headquarters are in Andalusia, but we have also some laboratories in the north. These are the areas and the sectors that are related with FLAMINGo. The expertise that we have is in product and process engineering, computation and simulation, advanced materials, digital technologies, and energy efficiency in transport. In this area, I would like to highlight, even if I don't have a picture, I can share with you the general presentation of the entity. We have a big format laboratories to test a complete train inside this cold tunnel, so we can reproduce rain, wind, snow. So, and we can test. We have now an accreditation for testing people within the train in this cold tunnel. So, just in case you have a use case with a big format, we have this capability for the energy efficiency. So within the advanced material department, we have this TED wire technologies and Meltio brand. If you know this Spanish manufacturer of manufacturing, we have robotic friction stir welding laboratory, metallography laboratory, and also the laser powder bed fusion and other polymer technology. So in this part, within the Munich project, as you may know, it's very difficult to process aluminum by DMD because the aluminum has a very high energy reflectivity. And one of the motivations that we had to propose these technologies, even with powder and wire in Munich, was that we can use cheaper material in the case of wire. It's a faster process. It could be the faster additive manufacturing processes. Right now, we have possibility of processing bigger parts, and it's a very clean process in general and safer. Okay, I'm talking about wire, DD wire, not with powder. So, in our case, one of the achievements that I would like to highlight, we could process aluminum in this Meltio equipment, even if the manufacturer said that we could not. So we are using only 1.2 kilowatts, and this is a really low energy source compared to the WAM technologies that people is using, which would be very similar to DD with wire. And in this case of one, they are using 16 kilowatts. So imagine the strategies that we have to follow to try to process the aluminum. But we could make it. Here you can see our bigger sample at this moment. We machined the tensile test and we tested. I didn't show the mechanical properties because they are even better than the conventional aluminum 63, 66, yeah, the aluminum, 63, 66. And basically, this is something that we want to publish because it's quite new and it's a very good achievement. Regarding the robotic friction stir welding, we are trying to weld the multi-material, but we started first with aluminum alloys itself. If you know this technology, it's a welding technology which not melt the material, it's working in the plastic field of the metals. So after the processing, the microstructure is very fine, equiaxial, and very homogeneous. In general, if you are controlling the parameters, you can achieve this microstructures with have a translation in a very good mechanical properties after. So here, for example, is the welding of the aluminum silicon magnesium in the right from prima additive manufactured from powder. So here you can see the typical microstructure from additive manufacturing, right, with the melting tracks, and then the starting part of the welding in which is very fine and very homogeneous, and we cannot see these big structures. So the latest development trying to join the composite and the aluminum made also by prima additive. This one is made by additive manufacturing display. We generate this mechanical interlocking in the aluminum plate, and then we try to flow the polymer, the reinforced polymer with carbon fiber within these holes, or texturing, we call it texturing. So we use this tool without any pin, because the pin was absolutely broken and making a mess within the polymer. So we use only a shoulder, and we friction it, generate the heat, and allowing the polymer to flow. This is the latest scientific paper, and the last slide from our side. We are also manufacturing in the DED wire equipment the tools for pre-existing welding, so we don't need to buy to a provider any tool. We can make it ourselves. We can change the design dynamically depending on the thickness of the blades to be welded. So so the results were very good. Okay, that's it on my side. Hopefully you find it interesting. Please contact us for any collaboration. We are ready to prepare the next proposals, which are going to be available soon, hopefully for next year and the following one. And thank you very much.
Thank you very much for the presentation. Thank you very much for the presentation. Are there any questions? We could have one, and then.
Thank you for that presentation. So, if I understood correctly, you first additively manufacture the aluminium, and then the idea is you friction stir weld it with the composite material.
We manufacture the aluminum components, the metal components, and then the carbon fiber composites on the other side.
Okay. Is there? Do you find any macro segregations in during the additive manufacturing process in the aluminium? Is there, for example, certain areas that have different compositions of particular elements or anything like that? Is this something which you see?
In general, by the moment we are finding really homogeneous material. I mean, it's not homogeneous itself, but more or less it is. But it is true that we are performing now chemical analysis in different points of the sample, so I cannot say exactly by the moment. It's in progress right now, because we are performing the thermal conductivity testing, also the chemical testing, and checking that it's repetitive, it's comparative, and it's homogeneous. So I will let you know.
Okay, thank you.
Thank you again for the presentation. Moving on to the next presentation, we have the Collaborat cluster by Rafael Afonso from Mina Maghreb, with battery projects joining forces to support the uptake of sustainable green mobility.
Good afternoon, everyone. Here to present, thank you. Here to present the Collaborat cluster, a cluster of battery funded projects. Starting to say that my name is Rafael from EWF, as presented by Basilis. I also work and collaborate with the FLAMINGo Project for the standardization and training activities. And I'm here today to share with you what has been the efforts of Collaborat, mainly in ensuring that the knowledge that is generated within these projects is not lost, and that future projects can still pick up on this knowledge and evolve further on what have been the development so far. So overall, Colabat cluster born as a way to collect, as I said, all the information from these projects funded under the same whole topic, and the cluster itself focused on different aspects of the battery. So the battery pack manufacturing itself, including the battery cells, the integration in the vehicle, so everything that includes battery management system and thermal management systems. From here, it includes also its use in repurpose and remanufacturing, including options for second life applications on those batteries. And finally, also related with this point, the part of the recycling of these batteries, so finding strategies to recycle not only the batteries in new applications, but also the chemistry of the batteries itself, and to understand how all the process could be enhanced to ensure what we need to have and is still lacking, that is a proper dismantling and repairment and retrofitting of batteries in different applications. So, as expected impacts of these projects, it can be summarized in these 4 points. So, obviously, to reduce the battery system weight by 20%, the effort aligns with FLAMINGo efforts in a way to optimize also the part of chassis components and its materials in a way to not only along with the batteries itself and the reduction of the increase of the energy density of these batteries, but materials together, materials from the chassis and structure together with the battery materials and the battery cell optimization allows to achieve this objective of reducing the weight by 20%. Another objective is to extend useful battery life to 300,000 kilometers in real driving. This is a really a big concern nowadays, and the Colabat cluster, what it's doing is discussing with all the experts that are involved here, what are the best strategies to ensure this objective, and this will depend on all the approaches that are followed for successful dismantling and repairment, but also in all the technical and electronic systems as the battery management system that is able to detect, to optimize charging and to detect defects in the battery and to compensate for those defects. This is the important work that is being done. And also to be able here to have discussions at the life cycle analysis level for the improvements in this topic, and overall to create and to improve knowledge on module and pack, including the thermal management systems, also a key part of electrical vehicles that we know that if we want to be successful in having an extended battery life cycle, we also need to be successful in the strategies that we use for the optimization of the thermal management system. So overall, there are, from the beginning, 4 projects that initiated this: the project Helios, Marble, Albatross, and Liberty. All of them go under the same route. So the objective is weight reduction, as I pointed out, reduction of charging times, and also the capability to improve the life cycle of these batteries. All of them expect and are trying to test them, the new batteries, the new developments in different platforms of vehicles. So from the utility vehicles, from normal commercial vehicles as the BMW i3, but also in the Mercedes EQC, but also in buses and public transportation, this is being used. So overall, to conclude the presentation, we have 4 main subclusters. Subcluster A, where we are discussing these topics of sustainability and life cycle analysis. The subcluster B on testing of the batteries and procedures that will then fit standardization and allow to have a common procedure for these operations, battery management systems to discuss the strategies for proper identification and optimization of the batteries itself and modeling of these batteries. We invite you to join us. Currently, we have not only the 4 initial projects, but also the CBET, the IBATMAN, and the INNO-BMS. What we expect for the future of this cluster is to pick up on the knowledge that we generated here and to continue the activities to have more projects and to find a common answer for all of these topics that are discussed in these different subclusters. Okay, so feel free to contact me. You have the QR code here, and thank you very much. Time for questions if there are any. Thank you. Yeah.
I have a question regarding the batteries. Was there any synergy or alignment with the digital passport for batteries? That it's the one that's being more advanced, or the first one that we're going to see for the.
We organized a workshop dedicated on this topic with all the main key experts from the topic, including the Global Battery Alliance, that is already doing a great job on this topic and defining some parameters. We expect to conclude these sessions. So this is part of the subcluster on the sustainability. Okay? So you are more than welcome to join. Thank you.
These are my questions almost as well. Well, the question from my side was related to the subclusters. If you could elaborate more. I mean, is this group open for other projects maybe to join different subclusters, or the existing 4 projects are divided in different working groups? This is the case, or maybe FLAMINGo or other projects are invited to join this cluster?
As we stand, and the current approach of the cluster itself is to have projects working with batteries, with electric mobility vehicles, so to be able to have a representative in all of these clusters. In the future, it's not closed the option to have people with a specific knowledge contributing to the different topics of the subclusters, because something that we saw is that internally in these projects is not always possible to have the most expert people on the topics that are being discussed. So this is also a possibility for FLAMINGo and others to join in the future.
Okay, thank you.
Moving on to the last presentation for today, we have again a visitor for us, presenting the lessons learned of the LITV.
Yeah, so also like EV is a cluster of projects funded all in the same call as the FLAMINGo, which was asking for, as I said this morning in the beginning, for many different aspects that contribute in a sustainable way to vehicle waste reduction. So these projects are Project ALMA, LEVIS, Revolution, Fatigue for Light, and FLAMINGo. So 39 proposals were submitted for this call, and these 5 have been selected. So all these projects were dealing with lightweight materials, advanced materials, recycling, what was that? Eco-design principles. So we had all the similar, equal goals in mind, but all dealt with this in a different way. So these 5 objectives has been identified as a summary of the different objectives from the projects during our first sessions of meetings and workshops with the cluster. So the main area of work has been advanced materials, cost-effective manufacturing, eco-design strategy, recycled lightweight materials, and also machine learning models, artificial intelligence-based models and sensors. But not all the projects gave the same impact, the same weight on these aspects. So, for example, Alma was more on eco design, and Fatigue for Light was more on AI-based models. And of course, all the aspects has been taken into consideration from all the projects, but in a different way. So yeah, okay. More examples here. So the project portfolio from India, which is an organization collecting all the results from the different projects and promoting also the different projects. So if you are curious about what has been developed in the area of green mobility by European Commission, these are tracked since 2010. But actually, if you want to really get an idea of which are the possible technologies, applicable technologies, it's very difficult to get it from these portfolios, because these portfolios are more about the project in general. So what we felt a bit missing, talking with the other projects, is a sort of repository of the different technologies that has been developed in the project. This could be useful to have a possible clustering of the different technologies for specific needs, and also this would benefit from benchmarking by using the SCA tools that we are developing in our projects. So these tools has been assessed quite well in each project, and they should provide comparable results that allow us to put all the materials, manufacturing technologies, more or less on the same page, on the same level, and being able to be better found from stakeholders. Other important factors is the sensitivity. So in some cases, collaborating with the other projects, we found some IP consideration has to be made. The property of the results is sensible, especially if big companies are involved in the project, because in some cases less reactive in deciding if something is worth to be considered secret, or it can be mentioned, or whatever, which is perfectly fair. So the sharing of the results is somehow hindered by this fact, and well, we don't have a solution for that, but that this is a topic that we considered worth to be highlighted, as well as scalability and cost effectiveness of materials. In some cases, also the other projects reported that even if good results are achieved at a lab scale, the scalability issue is still a big problem for the projects, for having a good exploitation of the results. And this should be probably considered since the beginning in the frameworking of a program or frameworking of a proposal. Like the cost effectiveness of materials, we should be affordable, considered affordable. So the sustainability is not only for the environmental aspects, but also for the economical aspects. Yeah, and that were the 5 takeaways that we discussed with the other cluster project in the cluster, and we wanted to share with you. So thank you.